I would like to welcome everybody at our Tracking and Its Many Guises workshop. So first, a warm welcome from the organizers. So my name is Alyosha. I'm a postdoc at Technical University of Munich, and I'm co-organizing this workshop with Achal and Tarasha that are already here, as well as Jonathan and Pavel. They will join us later. And I see that we have quite some participants here already, and I would like to welcome everyone, and I hope that more participants will tune in as the workshop progresses. So of course, feel free to use the chat. We would also like to encourage you to actively participate and ask questions to speakers. So to ask questions, so I got here a message that someone cannot hear me. Can everyone else hear me? I'm not sure if there is a problem on my side or on this attendee side.
Okay, someone said they can hear you. I can definitely hear you. Okay, yeah, it might be an issue with one particular attendee.
Mm-hmm. Yeah, so then I would here I think the conclusion is that the problem is on the other side. So so it seems that here everything is all right. Okay, so at this point, yeah, I was talking about questions. So feel free to use these Q&A options here and post questions, and we will answer your questions after talks. And now we will start with intro talk that will be given by Achal, and he will talk about state of object tracking, and he will also introduce the tracking any object challenge.
Yeah, it's a 7 a.m. my time, so I pre-recorded this talk, but I'm here to answer questions and things. But I think the pre-recorded talk will be more coherent than I will be right now.
So like just to add there, we are actually scheduled for like 2 hours for a 2-hour slot on ECCV, but we actually run for 2 hours and 40 minutes on this same session 1 link. So please feel free to stay back after the ECCV slot ends.
Yeah. Okay, so I will now start playing the video, okay?
Oh. First ever workshop on object tracking and its many guises. I'm Achal, over here on the far left, and I'm co-organizing this workshop with Tarasha, Pavel, Jonathan, and Alyosha. As the name suggests, we're here to talk about the state of object tracking. As you probably know, object tracking is critical for lots of vision applications. Maybe the most popular right now that we hear a lot about is autonomous vehicles, but tracking is also necessary for a wide variety of other tasks like forecasting, sports analysis, or action recognition. Despite its importance, tracking is kind of fractured into a few different subcommunities, including 2D multi-object tracking, which requires detecting and tracking all objects in 2D, and its 3D counterpart, as well as user-initialized or single-object tracking, which requires tracking a single user-specified object throughout a video, and its segmentation counterpart, video object segmentation, just to name a few. These tasks all share the fundamental goal of tracking objects in videos, but vary in small ways in their setup that lead to different communities building approaches specific to the particular task. Our goal with this workshop is to bring these communities together towards building robust general-purpose trackers that are useful for downstream applications. To encourage some spirited discussions in the next few slides, I'll talk about some of my biased opinions on why we haven't been able to build such general-purpose trackers. But don't worry, we'll also hear from a number of invited speakers soon afterwards who will possibly have differing opinions. First, what do I mean when I say we don't have general-purpose trackers? Well, today, when someone asks me how to detect and track various objects in an arbitrary video, my go-to response is the following. Download and run the best image-based detector you can find, like, say, MaskRCNN, and then run a simple heuristic-linking step on its outputs. In fact, despite the rich history of object tracking research, when people want to use tracking for downstream applications, this heuristic strategy is often their preferred solution. But we know this strategy is far from optimal, so why don't we have more powerful generic trackers that can be easily used in the wild? One reason that I think might explain why tracking is in this state is that we often tackle auxiliary tasks that aren't directly useful for downstream applications. For example, user-initialized or single-object tracking is an extremely popular area of research. Here, the goal is to track a single object specified by a user with, say, a bounding box throughout a video. This task has clear applications in video editing and data annotation, where we have access to a user or an oracle who can initialize the tracker. But can it be used for more general tasks? Many papers claim that it can be used for a much more diverse array of tasks, like autonomous driving, or augmented reality, or unmanned system. We've even made this claim in one of our projects before. But in reality, this task is limited to applications where human input is available, which precludes lots of important vision and autonomous system applications. Of course, this isn't the only problem. We do also tackle the more generic task of multi-object tracking, where all objects from a vocabulary are detected and tracked without any human input. But when we do this, we usually build application-specific trackers. And what I mean by this is we have a set of approaches for tracking people from a single camera, another set of approaches for tracking objects on the road from car-mounted cameras, and another for re-identification from multi-camera setups. In fact, this strategy is often encouraged in the community, as you can see in this anonymous quote from a reviewer who says, "I don't think that a good tracker can or should work in the wild." By contrast, I'd argue that aiming for general-purpose trackers is important and will naturally lead us to robust methods that also adapt well to specific application scenarios. In fact, this strategy of aiming for general-purpose solutions is arguably one reason that other vision fields like object detection have been so successful. However, even if we decide to build general-purpose trackers, we don't actually have strong benchmarks for measuring how well these trackers work in the wild. Again, unlike image-based communities. Specifically, we usually evaluate our trackers on benchmarks that tend to be small and focus on a few specific domains. For example, the popular MOT dataset evaluates trackers only on people. Similarly, Kitty evaluates trackers on people and vehicles, while ImageNetVid evaluates on animals and vehicles. And other datasets are similarly limited, ignoring the vast diversity of objects in the real world. So given some of these concerns, how can we build useful trackers that can be used by practitioners and researchers who want to use tracking? I'd argue that the first step is to build general-purpose trackers that work not only on diverse objects and scenes, but that can also solve multiple tasks simultaneously, whether that's multi-object tracking or single-object tracking in 2D or 3D with boxes or with masks, and so on. Next, to really measure progress in this direction, we must evaluate our trackers in the wild in as many diverse scenarios as possible. Towards this end, we've collected a new dataset, Tau, which contains a much more diverse sample of real-world videos and current benchmarks, which we'll discuss later in this workshop. Of course, like I said, these are my views on what's holding tracking back. Over the course of the day, we'll also hear from various invited speakers, including Leal Taixé and Jiri Matas, who will discuss where multi-object and single-object tracking are now and where these fields are going, as well as Cordelia Schmid, Bastian Leibe, Deva Ramanan, who will talk about the role of tracking in various downstream tasks. Finally, we'll hear from speakers outside the traditional tracking community, namely Anju Kanatsawa, who will talk about 3D recognition in videos, which we believe will be an important aspect of building robust trackers, and Ross Gershik, who will discuss lessons learned from the image-based object detection world. Our schedule is as follows. After this talk, we'll hear from Cordelia Schmid, followed by the winner of the Tau Challenge, followed by Leal Taixé, and talks from Jiri Matas and Bastian Leibe. And then in the second session, we'll hear from Anju Kanatsawa, we'll have a roundtable with some of the speakers, and then a talk from Deva Ramanan, and then Ross Gershik. Before we move on to invited speakers, I'll introduce our new tracking dataset, Tau, and results from this year's first ever tracking challenge on our dataset. Tau is a large-scale benchmark for tracking any object. As I mentioned earlier, a major hurdle with progress in tracking is the lack of diverse benchmarks. Current datasets like the MOT, Kitty, and ImageNetVid datasets, as well as others, tend to be limited to a few specific object categories, and they ignore the vast diversity of objects in the real world. Our new dataset, Tau, does evaluate trackers on such diverse objects. In total, Tau contains over 24 hours of in-the-wild video used for evaluation, which is more than 6 times larger than previous datasets. To collect this dataset, we address 3 key challenges. First, how do we select a representative set of videos on which to evaluate trackers? Next, how do we construct a vocabulary of objects which are important for tracking? Finally, given the unlabeled videos and a vocabulary, how do we scalably annotate objects? We start with the first question. Collecting diverse videos is a challenging task. Simply searching for objects and scenes online does not result in realistic videos. Given this, how can we find representative videos where we would like trackers to work? To do this, we instead turn to existing video benchmarks. Specifically, we use 3 action recognition datasets: the AVA dataset, which contains movie scenes with multiple actors and objects, the HACS dataset, which contains videos posted online of people performing various actions, and Charades, which contains indoor videos of scripted actions. Next, we include outdoor videos from autonomous vehicle datasets, including Argoverse and BDD100K, as well as unstructured user-generated videos from the LA SOT and YFCC 100 million datasets. Sampling from multiple datasets provides us with a diverse selection of videos which represent common application settings for tracking. If trackers work on these videos, they should be useful for downstream tasks. Next, we address the question of vocabulary construction. The usual approach for constructing a vocabulary is to manually write down a list of categories that we care about. We may decide that people, cars, and bicycles are important and add them to the vocabulary, and later realize we also wish to track animals. After deliberation, we can arrive on a fixed list of important categories. However, this vocabulary is naturally biased, often small, and may miss important objects. Instead, we discover the vocabulary from the data in a bottom-up manner. We start with an unlabeled video, such as this one, and ask annotators to select moving objects in the video and label them with tracks, without a particular vocabulary in mind. Given these tracks, we then label each object with a class label, either from the large Elvis vocabulary or with free-form text. Finally, we add these labeled objects to our vocabulary. Our approach uses motion to discover relevant categories, which may have been overlooked even in the large Elvis vocabulary, such as an e-book reader or a Nerf gun. Given this vocabulary, we must now label the entire dataset with these categories in a scalable manner. However, labeling every instance of every category is prohibitively expensive and often unnecessary, as in this video. The standard protocol for labeling would have to simply drop such videos, as labeling every person in the crowd is expensive and potentially ambiguous. Instead, we choose to label Tau in a federated manner, which allows for labeling a subset of instances in each video. Given these labeled instances, we can then collect auxiliary labels, which indicate which categories are exhaustively labeled in the video. For example, in this video, we can mark that towels and bottles are exhaustively labeled, while people are not. We can additionally mark categories which are absent in the video, such as cars or elephants. Using this information, we can then measure the recall of trackers on all present categories, whether they're exhaustive or non-exhaustive, while only penalizing precision on categories which are exhaustively labeled or absent. Our choices in addressing these challenges were critical for collecting a large-scale dataset, ultimately resulting in Tau, which contains nearly 3,000 videos collected from existing video datasets, with a vocabulary of hundreds of object categories, and labeled tracks for over 17,000 objects. Next, we use Tau to analyze the current state of tracking approaches. To do this, we first introduce our evaluation metric, which is inspired by object detection. Mean average precision using 3D intersection over union, or IOU. While object detection metrics compute the 2D IOU between a ground truth box and a predicted box, 3D IOU computes the total overlap between a ground truth track and a predicted track across the video. Using this metric, we evaluate approaches from 3 subfields within tracking. First, we evaluate multi-object trackers, which aim to detect and track all instances of a fixed vocabulary. we evaluate two strong baselines for multi-object tracking, namely Viterbi and Sort, which perform well on the popular ImageNet and MOT17 benchmarks, and find that they struggle on tau. To better understand this low performance, we analyze common failure cases. First, we find that a frequent error is due to broken tracks, where an object is correctly detected but incorrectly tracked in the video, either due to occlusions, as with the toilet on the left, or due to camera motion, as with this person on the right. To analyze the impact of such errors, we apply a linking oracle to the outputs of a per-frame detector. This oracle perfectly links the detection outputs of an existing detector and provides a strong improvement over the baselines. This suggests that even with current detectors, better trackers can lead to significant improvements on tau. However, even with this oracle, performance remains low. We find that a major cause of this is due to the large vocabulary of tau, which causes trackers to struggle to classify across the many categories, as evidenced by the consistent misclassification on the left, and semantic flicker between a camera and a hairdryer on the right. To analyze the impact of classification errors, we evaluate using a classification oracle, which fixes naming errors, such as calling a canoe a surfboard. We find that this oracle strongly improves the performance of both the baseline methods as well as the oracle linker, indicating that tau requires improved large vocabulary classification through tracking. Next, we evaluate a subset of approaches which are focused on tracking only one particular category, people. We start by evaluating the generic trackers from before on the person category, and find that even generic trackers perform better on people than other categories, likely because people are easier to detect and track than more challenging objects, which may be small and undergo frequent occlusions. Additionally, we find that a method that's tuned to track people, called Traktor++, strongly outperforms generic trackers, suggesting that a key open challenge is generalizing such trackers to all categories. Finally, we evaluate user-initialized trackers, or single-object trackers. These trackers aim to track an arbitrary user-specified bounding box, as shown on the left, throughout the video, without needing to know the object label or any fixed vocabulary. A key goal of such approaches is to generalize to uncommon objects. We use tau to evaluate progress towards the skull. As these trackers do not report a class, we evaluate them using a classification oracle. Since user-initialized trackers employ more powerful machinery, including re-identification, they perform better than out-of-the-box multi-object trackers, such as Sort. However, they provide little improvement when compared fairly to multi-object trackers equipped with a classification oracle. This result suggests that large vocabulary multi-object trackers can perform on par with user-initialized trackers without using any initialization. Our results suggest a few important takeaways. First, generic multi-object tracking performs surprisingly poorly on tau due to the diverse and challenging scenarios in our dataset. While focusing on a specific scenario, such as tracking people, can improve performance, generalizing these improvements remains an open challenge. And finally, while classification and tracking oracles are helpful, manual initialization is not nearly as helpful as we might expect, leading large vocabulary multi-object trackers to perform on par with user-initialized trackers. These results show that tau presents unique challenges due to its diversity and large vocabulary. To encourage more robust, generic trackers that work in the wild, we've also organized a challenge over the past couple of months on tau. Our challenge evaluated trackers on nearly 1,500 test videos in tau with held-out labels. This challenge was organized on the MOT Challenge website, and we'd like to thank the MOT Challenge team, and particularly Patrick, for his help in running this challenge. This year, we received a total of 7 submissions, and we're pretty excited about the results, as they've really pushed up the accuracy of trackers on tau. Let's take a look. On the test set, our baseline using the Sort tracker achieved a low AP of 10.2. In third place, we received an anonymous entry which significantly improved the AP from 10.2 to 14.2, while the second place tracker took this further and improved results to 20. Finally, we'd like to congratulate the winner of this year's challenge, Fei Du, whose submission improved AP by over 17 points from the baseline. Congrats, Fei, and we're looking forward to an excellent talk from Fei on a submission later in the workshop. To all of you, thanks for attending our workshop, and we hope you'll enjoy all the talks we have lined up. Please do check out the workshop website to stay up to date with the schedule. Thanks again.
Okay, so next on our schedule is will be invited talk given by Cordelia Schmid. Cordelia is not here yet. Let's wait a few more minutes, and meanwhile we can answer some questions. Charlie, will you take that over?
Yeah, sure.
So do you want me to moderate the questions?
No, I think that's fine. I can read the chats directly. Let me just. I'm wondering if I should send Cordelia an email, or do one of you want to do that just in case? I think I sent her a calendar invite, so she should know. But yeah, all right. So I'll just address the questions. I'm sorry if there's some background noise. The AC just started. All right. So first is. Could you elaborate on the re-ID ability of objects? Was that improved? Yeah, so this is a good question. In general, we didn't try to improve any methods compared to, like, we basically took published methods and evaluated them to see how things are doing right now. So most of the methods in multi-object tracking that we evaluated didn't actually do re-ID. So like sort and viterbi don't do any sort of re-ID. Traktor++ does do re-ID. And I think that's one of the reasons it works so much better than sort and viterbi. And then single object trackers implicitly do re-ID, but we didn't touch that. We just left it as is. The next question is, sorry, I just got an email from Cordelia. She wants the Zoom link. Let me send that to her. Sorry, I need to find the Zoom link now.
I pinned it on our chat on Slack if you want to find it.
Oh, okay, I found it. All right. Okay, I've sent that to her. All right, the next question is it possible to explain what Oracle linkers are? Yeah, so it's kind of like the simplest thing you could do. So you take the outputs of a detector on every frame, and you compare each detection to the ground truth that you have, and you just assign the ground truth track ID to that detection. So what this means is you perfectly link together detections in the best possible way, such that if you at least recovered the location of the object, then the track will work. And the track will correspond to the ground truth track. I'm happy to keep answering that in the chat later as well if that's still confusing. One question that I think seems important. Oh, there may be some questions sent to all panelists only. Could the organizers make the questions available? Yes. Tarasha, do you mind doing that? If there are any questions that are sent to all panelists. Yeah, by default, if everyone could send questions only to all panelists and attendees, that way everyone can see the questions.
Yeah, I think the best thing to do is post everything on Q&A, so we also have a track of which questions are answered and which are not. And like everyone can see them also.
Okay. All right, I'm gonna take maybe 2 more questions because there's actually a bunch, so that we can, or I'll take questions until Cordelia. Oh, I guess Cordelia has just joined, so I'll take 2 more questions. This is a question that I really like. What was the reason for using only a small amount of data for training? So this is something we actually had a lot of discussion about. We went back and forth, and we have 3,000-ish videos. And ultimately, we came down to only using 500 for training and everything else for validation and testing. This is a very carefully chosen decision that I don't think everyone will agree with me on this. But the reason for this is I think we actually have lots of different sources for training. We have single object tracking data where you can learn how to do re-ID. We have data sets like COCO and Elvis where you can learn how to train detectors. And there's also a lot of push on learning self-supervised and unsupervised trackers. So in my view, training data is a problem for tracking, but I think it's a much bigger problem that we don't have kind of diverse and stable evaluation. So in my view, collecting a large evaluation set, which gives you a trustable number for your tracker, is right now more important than training. But of course, you know, one of our goals is to eventually expand this so that we have a much larger training set. And then the last question I'll answer is, can Tractor++ be extended to generic classes by training the detector employed there on additional classes? Yes, this is possible. There are some constraints. So one thing is like Tractor++ does use re-ID, and the re-ID is only trained on people. And it's unclear how that re-ID would work for the other categories. But you're absolutely right that theoretically, if you take out the re-ID part, the rest of it can be applied. But at that point, it's fairly similar to sort with a little bit of modification. So we didn't explicitly try that. But I would be curious to see how that performs. I'll look through the other questions just to see what they are, if there's anything urgent. Okay, I'll try to address the rest in the chat myself, and then we'll move on to Cordelia's talk now.
Hi, Arsha. Can you hear me?
Yeah, we can hear you.
Hi, Cordelia.
I cannot start my camera, but maybe it's not necessary. I don't know.
I think Alyosha will promote you to co-host, and then you should be able to.
Yeah,
Yeah, I did already.
yeah, he just promoted Cordelia to being a co-host, and now I think you should be able to turn on your camera.
Oh, it works.
Okay.
Yeah.
Great. And I'll also share my screen right now.
Mm-hmm.
Yep.
Before sharing your screen, I would like to ask you to tick two options that are at the bottom of the sharing screen options. They're called share computer sounds and optimize screen for sharing for video.
Can you say that again, please?
When you click the share screen button, then the window will appear, and on the bottom there should be two options that you should tick, and they're called share computer sounds and optimize screen sharing for video.
And which one? Yeah, should I see which one do you want?
Both, please. That are official instructions that we got from ECCV organizers.
Okay, sure. Okay, fine. Shall I go?
First, I would like to introduce you. So it is my pleasure to announce that we will start this session with a talk from Cordelia Schmid on tracking as the missing piece in video analysis. So Cordelia holds a joint appointment with INRIA Ron Alpes as research director and with Google Research. Cordelia obtained a master's degree in computer science from the University of Karlsruhe and a PhD from Institut National Polytechnique de Grenoble. And afterwards, she was a postdoctoral fellow in the robotics research group of Oxford University. Among many achievements, Cordelia was awarded with the Humboldt Research Award in 2015, with the INRIA and French Academy of Science Grand Prix in 2016, and with several prizes for fundamental contributions in computer vision that have withstood the test of time. Cordelia, we are really excited to hear your talk.
Okay, thank you for the nice introduction. Can you hear me?
Yes, we can hear you.
Okay, fine. Let me know if anything goes wrong. Okay, so my talk is tracking the missing piece in video understanding. And so what is the task of video understanding? Ideally, what we want to do is to completely describe the story of a video. So for example, here we have a movie and you would like to say, as the head waiter takes them to the table, they pass by the piano and the woman looks at Sam. Sam, with his conscious effort, keeps his eyes past the keyboard, and the head waiter sees Ilsa. Right, and basically to do so, what do we need? We need to recognize what are the actions in the video, but we also have to have the whole content and interaction between people. And so basically, if you look at this, if you really want to describe this precisely, you need to follow the people and track them in the scene, right? So basically, if you only go on the frame-based level, you don't know how the people interact with each other. If you have the spatial temporal features, you can capture locally what people are doing. But if you really want to measure the interactions, the belief here is that you need to track them. And similarly for the objects, if you want to have the interactions with the objects, you need to track them. Okay. And then here's some other examples. So for action classification, here you don't really need any additional information. So here basically it can be based on lower level features and classification, good enough. But then if you want to go further, and for example, for self-driving cars, you want to see where the pedestrians are and what kind of activity or action they're doing. So for example, here, the person is going to cross the road, so the car has to stop. We do want to understand precisely where the person is, and to do so, we need to localize, detect, and track it. And similarly for video surveillance. And so here, maybe just the word, what we want to do is not just standard tracking. We want to also assign a category label, and then maybe even more fine-grainedly an action label of what the person is doing, right? This is one of the things which we have introduced in the tower data set, is that we go beyond just tracking, but it's really video object detection. So we want to detect what category the person is, then track it, and then ideally here also determine what kind of action the person is doing. And then here, just an illustration of the spatial temporal action localization. You want to see at which moment in the video the person is drinking, where the person is, and detect the time interval, right? And then, so here, a second example, brushing teeth. Then ideally, as I said in the beginning, we would like to go even further and really describe what the person is doing, drinking, talking, sitting, and so basically have the full story connected together. And so what are general methods for spatial temporal action localization? So basically methods, they kind of for small time intervals, so clips or frames, to determine where the action is, and then link the actions together. So here comes in the tracking. So either the tracking is done beforehand or after, but at some point you have to continue, see how the action continues over time, and then they're rescored on temporally localized. So this is kind of the general framework today. As you can see here, the tool is the part where the tracking comes in, and in our ECCV 2015 paper, we have shown that actually having a better tracking can improve significantly the accuracy of the spatial temporal action localization. And so, as I said before, state-of-the-art methods. So here we have developed a state-of-the-art method and applied to the AWAS dataset. What they do is they extract short time intervals, clips for short time intervals, localize the people there. That's the research proposal network, and then apply 3D filters to classify the action into different categories. So for here, example, we would have walk, stand, carry, and hold. And then we can look here at the results. Okay, fine. So what we can see is that actually the temporal interval is important. So if you have a longer temporal interval, the performance improves. But we can see that the accuracy on this real-world AVA dataset is still quite low. And so one of the things which we have then introduced is to have a better tracker and a better localizer of the objects. So here, two parts. Basically, if we can track the person, we can determine what kind of different small actions come into play when doing the action classification. And then if we have the interaction with the object, we can in addition say what type of action the person is doing. So if you look at the false answer for shaking hand, we can see here, the person is reaching out the arm, but is not shaking hand, but he's touching another person. So to determine this, we need to have a more temporal continuity, but then also localize objects and track objects which are, or interacting persons which are in the frame. Then similarly, the second example, false answer for smoking, the person is just kind of covering the hand. There's no cigarette in the mouth. And so one approach which we have introduced to address this is a structured model for action detection. So here we have an input video. We perform object detection and actor detection. Then we use actor tubelets, so we track the actor over a relatively small time interval. We have a relation graph where we determine which objects the person is interacting with, and then we get the output. And so here, what's important for the temporal determinacy learning, we want to construct the tuplets based on the parent similarity of the objects. This is a relatively small, simple tracker, very lightweight, but obviously here, again, if you had a better tracker, it could come in here and it would further improve the performance, because as we will see, the better the tracks are, the better is the performance. And then we show here that if we combine the features in the tuplet with the graph convolutions, we can improve the performance, because then we see what is the sequence of very short actions and how they interact with each other. And then similarly, we have a graph which models the human-human and human-object interactions. It's trained in a soft-definement way, so it's not labeled. And basically here again, if we had better tracks, we could further improve the performance. We can see that our actual tuplets plus sub-relation graph improves significantly over state-of-the-art approach by more than 6%. And then if you look at examples, here on the left, we can see the action is classified incorrectly as sit, because it's kind of a downward motion. And then if we use our approach, which models the temporal dependencies inside this action tuplet, we can correctly label it as fall. So here we can really see that the sequence is first the person stands and then it lies on the ground. So basically the falling action is modeled in the middle, while if you just average the features, it looks like somebody is sitting down. And then here an illustration of the relation modeling. So we can see that basically by adding the relations, the baseline would classify the object, the action as hold, because the person is just holding something. But then if we model the interaction with the fork, we can actually determine that the person is eating. And so here again, it's important that we find these objects, and if we have a better continuity obtained by tracking, we would further improve the performance. Okay, here just a small overview of the results. So here ours on the right and then the baseline on the left. You can see the example of falling, which we've seen before. Then eating. So here again, it's important not only to model the interactions, but also the temporal sequence. And then another example for fighting. So basically, if we only model per one person, we don't know the interaction, we cannot model the fighting action. So here we have seen that basically the tracking is important to model the continuity of the action, the interaction of the object is important. So now show a second example where again, the detection and the tracking of humans plays a key role. So what we want to do here is we want to learn action localization with varying levels of supervision. So the idea here is we only have the labels for the full clip or even for the full movie, and then we want to determine where in the movie the human is performing the action and which is the actor. And so basically the annotations can be either on the video clip level, it can be for one frame or for a temporal interval. In all cases, we need to complement the information. And so what's important here is first to extract the human tracklets and then assign the human tracklets to action labels. And what we'll see in the results is that one thing which is very important is the quality of the tracking. If the tracking is bad, then the tracks get broken up often and the assignment quality is bad. And the second thing which is obviously important is the quality of the descriptors. And so we have had a previous approach which also attacked this problem, but at the time the tracker and the descriptor were really bad, and so this made the problem much harder. And so here what we have obviously also introduced is a novel formulation based on discriminative clustering, which helps to disambiguate, but the main key components are actually the tracking. And so what is the approach? Our person tracks are obtained by the automatic detection and linking, and then tracks are subdivided in small elementary segments called tracklets. And then what we want to do, we want to assign to each tracklet an action class. So we have, say, 10 actions, and we have 10 actions plus a background class. So basically each human, let's say we only extract humans, assume the tracker is good, we only have humans, so we want to assign each of these tracklets to either a human action or to the background class. And so to do so, we have introduced an extension of the discriminative clustering. Discriminative clustering learns at the same time the classifier. So here we have the W is the classifier, and X would be the tracklet. So basically what it learns is how to which cluster to assign the tracklet and how to join the classifier. And then person tracks have different variants for extracting the person tracks. They are extracted with faster RCNN and then online linking. And then we have a variant where we actually fine tune the person tracker and perform the tracker with KLT. For the tracklet feature representation, we use I3D features, RGB, and optical flow. And the datasets which we use for evaluation is the UCF 101-24 category dataset and DALI. So the difference between the two datasets, UCF 101-24 categories, it's relatively short video clips and only 24 action categories. DALI are much longer videos, but the number of categories is only 10. Okay, and so now if you look at the results, so there are two state-of-the-art approaches, 27 and 29. And if you look at the results, we can see that basically on the full left, if it's completely only, the supervision is only at the video level, we get relatively low performance. So UCF 101, we had 43%, and DALI at 7.6%. So what we measure here is we perform the weak supervision on a training set and then evaluate it on the test set. And at 0.2 is the overlap threshold, right? So it's the overlap threshold in space and time. And so if we look at the different points, so we can introduce different levels of supervision. So for DALI, we can obtain results for the shot level supervision. So video is several minutes long. Then we can extract shots, which is around a minute. We can see that adding tempo supervision, so to say roughly where in the video the action is localized, gives us an additional cue, improves the performance. Similarly, saying which tempo interval is important gives us a further improvement. And if you look at the column which says tempo, what we can see here, there are results given in parentheses. And the results in parentheses actually are obtained by fine-tuning our tracker to the data set. So what we're using here is the detector, the human detector is trained on the COCO set, and then basically for tracking, it's a simple association. However, if we fine-tune on our detector on the data set, we can see that this results in a significant performance improvement. And so this is actually the case, especially for UCF 101, because the quality is quite different from the COCO data set, and so actually the detection results and tracking results are quite bad. And so this really shows, for DALI the difference is not that big, but this really shows in both cases that if we had, and it's not a perfect tracker, right? It's just a better tracker. If we had a perfect tracker or a further improved tracker, our results would improve even more, right? And then the same thing for tempo and one spatial point. You can also see for hours the results in parentheses is by using a fine-tuned human detector. So again, what we can see here is that the things which are difficult is the imprecision to the human detection, which degrades our results, and then the other thing which is problematic if the video clips get too long, right? If they're too long, as for the DALI dataset, then there's too much confusion. And then we would have to have a better model for the interactions between the humans. But in all cases here, we're just looking at these small temporal intervals. What you really would want to do is to model the information over the full range of videos. And then here it would be important to have a tracker and an associator which can track the person over the video. And then here, if you look at a few results, you can see here the tempo predictions weakly supervised for drinking. We can see at the shot level, and then at different temporal and bounding boxes improves the results. Similarly for cleaning window. And then here for UCF 101, we can also see here the precision of the different approaches. And then one thing is, which is nice of this approach, that we can mix, actually the formulation allows to mix different levels of supervision. So we can have only the video level supervision, which is in the graph on the left. We can see here the results for DALI are pretty low. But then if we add 10% of annotations to these videos, the performance goes up significantly. So it's nice that this discriminative clustering formulation allows you to mix different levels of supervision. And so what we have seen now in both approaches is that actually it's important. The quality of the detection is important. So we have seen for the weakly supervised learning, the main thing which is important for a good performance. So basically the theoretical formulation is nice, but if you really want to improve the performance, the tracking has to improve. And then similarly for the first example, the DALI data set, the tracking is very difficult. And again, if we could have better tracks, we saw that having this track list improves the performance, but if we could have better tracks, we could further improve the performance. And so my last example here is actually for self-driving cars. So here, in contrast to the two previous approaches, extraction of the cars and the moving object is relatively simple, or is given basically, because you have this LiDAR information and they have very good systems for extracting the self-driving cars. You can see here the boxes there, almost all of them are localized perfectly. And so here you can really build up on, I wouldn't say it's perfect, but high quality tracks. So once you have these high quality tracks, you can then introduce a model which models the relations between different objects and in the environment. And so here, what we have introduced is VectorNet, and what VectorNet does, it takes the cars and the tracks and then maps them to vectors. Actually, each object here is represented as a vector of the displacement. So you can see here, you have the cars tracked, and then you map them to the displacement of the different cars. Here you see in red the car which you're interested in, and in the neighborhood you can see the other cars which are moving simultaneously. And so basically what we do here, we map not only the cars but also the environment. So basically we use polylines, points, polygons, and curves to represent the environment. And then once we have this representation, we can then map it to these polyline subgraphs. And as you can see here, such representation is only possible because we have good tracks extracted from the data, right? So if you could obtain something like this from movies, then you could go much further and model also these subgraphs. But for movies, this is completely impossible today. While for the self-driving car environment, where you have these cars, which is relatively representative, simple class, it is possible, okay? And then once we have this polyline subgraphs extracted, we can then model the interaction between the different cars and the environment with a global interaction graph. So basically now we can connect all the different components with each other and see how they interact with each other. We can then train this on a large number of supervised training examples, use two losses, L1 loss for target trajectory prediction, and the mask completion loss, where we mask out random features from the graph. And then we can test it, for example, on the Argoverse motion forecasting dataset. We have approximately 300,000 5-second long sequences. They include vehicle trajectories. The vehicle trajectories, they're extracted automatically, so they do include noise, but not a lot, and the map information. And then 0 to 2 seconds are used for observations, and the 2 to 5 seconds are used for prediction. And then for measurement, we use the average displacement metric in meters and the displacement average at t. And so what we can then see, if we only use the path trajectory of the vehicles in L1 loss, you obtain displacement error of 5.2. By adding the map information, you get an improve of 2. And then by adding the other vehicles and the map completion loss, we get a further improvement. So here what is nice, we can really see that the tracks which we have are good enough to really model the interactions between the other vehicles and with the world. And so here the world model is based on an HVD model. So for the cars, again, you have this very good world model. And for movies, if you want to go for movies, you could imagine obtaining something similar if we had good tracking components and then could connect the different tracked components with a structured model. And then what we can see here, you can see that our VectorNet approach compared to state-of-the-art convolutional network reduces the computation time, the number of parameters, and results in a better than 18% better performance. it's actually nice to show if we have this good model, we can then imagine good structured model which can take into account these interactions between objects. And then here we also compare to the state of the art, so you can see that our approach outperforms state of the art. And then basically what we have seen with these 3 examples in my talk is that it's important to have high quality human and object tubes and to model the environment correctly. So if you see the EVA approach, the EVA results are weak, still weak, so it's like the best results are currently 30% MAP. And what would help probably to model better the understanding of a video would be if we would be able to track the humans and the objects in the scene and to correctly extract them. And if you look at the results which we obtained for EVA tracking, they're still far from perfect. And one of the problems is obviously that you have a lot of shot changes. And so what you need to do is to be able to follow the people across these shot changes. So basically you have human tubes which take into account the shot changes and still follow the people correctly. And then we have seen the 3rd example has shown that basically once we have this almost perfectly extracted components, they obviously have still some noise and still further improvable, but then we can really tackle and implement better models which take into account the interactions between the objects, between each other, the object and the scene. And so what we have seen also is that tubes include detection, classification, and tracking jointly. So we don't want to only track, we want to really also detect and even classify, right? So basically what you would want to say is maybe even go beyond just saying this is a person, but you might want to also say what the person is doing at a specific moment in time. And so the detection and the tracking jointly, also classification is measured in Tower. So Tower goes beyond traditional tracking data sets in that it really evaluates these 3 components jointly. And I guess this is really the future for tracking. It's to go beyond just initializing the box in the first frame and tracking it over the frame, or just specializing for a few categories such as human and cars, but to go beyond this and really extract these object tubes, video object tubes automatically. And so once we have these video object tubes extracted well, we can then build on existing models to model how this object interacts with each other and what is really going on in the video. So ideally, what I've seen shown in the beginning, we want to go away from just classifying action instances, but really describe what is the content of a video. We've also seen a number of newer models which take into account spatial and temporal relations. We've shown that these models in all cases improve the performance. And then we have also seen that one thing where these tubes are important is for weakly supervised training and mixed training. So if we have these tubes, we can, for example, another talk which I gave this morning, we can then mine videos automatically and go one step further to really localize in these videos where the people are performing the actions. Okay, thank you for your attention.
Thank you very much for this very interesting talk, Cordelia. So I think now we have time for a few questions. So here in the Q&A session, I don't see any open questions right now, but I have a few. So I would like to start with that, if that's okay.
Sure.
Yeah, I think someone also raised, just a note, someone raised their hand. I don't think we can actually do anything if you raise your hand. So I think you should just type your question in the Q&A, because I think getting you on audio is a lot of clicks. So the best thing to do is for you to type the question. Sorry.
Yeah. And meanwhile, this participant writes a question. I will then start with mine. So the first question is about action detection with varying level of supervision. So there, it was very interesting lesson for me that the quality of tracking turned out to be really important there. And you have also presented interesting tracking pipeline that you used in this approach. And I was wondering here, did you also try out any of existing well-performing trackers, some trackers that perform well on the mod challenge, for example? And if you try them out during while working on this project, maybe it turned out that they for some reason don't really generalize to scenarios that you have had.
Yeah, so we didn't do a full-fledged study of like all existing tracking algorithms, but we did experiment with some variants. And so what we found is in this case, I mean, this is specific, right? Because it was only 2 data sets, right? So we had this UCF 101 and then the study data set. And what we found was that for the UCF 101 data set, the human detection was very weak. So it wasn't actually the tracker per se, it was the detector, right? Basically, what we also showed in our tower work is that basically it's important to have a good detector and a good tracker, right? If the detector fails, then the best tracker cannot like make it work anymore. And so that's what we found. And I guess what I would say in hindsight is my lesson here is that UCF 101 is a very specific data set. People are like swinging all the time. They have very different poses, which makes it really hard. Basically, this is kind of the lesson that in this case, the detector doesn't work. Study is much easier because there people are many in state-of-the-art poses. This is like the first thing, the detector is very important. And then basically the second thing is maybe that you also want to have some kind of adaptation of your optic detector tracker on the data, right? Because basically you don't want to go and label everything, but let's say we have an approach which works quite nicely on our current tower data set, but then maybe we take UCF 101 and we see that it's not working that well. And so what we really would want to do here is to have some way of weakly supervised adapting the tracker, right? And I think this is maybe the main lesson here is that if the problem lies in the data, then we would need to find something which adapts on the fly to the data. And I think these are current approaches which people are currently interested in, is how to actually fine tune or meta learn something on the current data and adapt it there. So that would be my lesson in hindsight.
Thank you.
I also have a question, if we don't have a Q&A yet. I guess one thing is, like, I feel like 3 or maybe 4 years ago, it seemed like the push in the action recognition world was really kind of end-to-end, like taking the CNN hammer and applying it to videos with C3D and I3D. And it seems like more recently, we're seeing more of these kind of structured or compositional models that, you know, you either do some sort of tracking first and then you do recognition. I'm curious if there's a reason that like the CNN hammer hasn't worked as well in action recognition and we need these structured models, if you have thoughts on why that's necessary, or if that's, you know, it's just a matter of time before we don't need to separately do tracking. Does that question?
I think that's a good question, but I think complexity-wise, I mean, one thing is obviously complexity-wise, right? Because if you have 1 hour of video material, you can just not feed the full hour in any end-to-end trainable structured model. So basically, we had recently this work on Video Bird, where we feed in visual features and text features, but even there, if you want to have any structured information which is coming out, it gets very, very heavy, and it's really clear you cannot learn it for more than a few minutes of time, right? So it's very hard to kind of automatically learn what are the relevant objects from some kind of end-to-end learnable representation. So you could not just say, I give the video the transcript and then it learns. It's probably not possible. And the second thing is, for videos, the annotation quality is quite low, right? So basically, we don't have videos like the first example which I showed, that you really have the video and the subtitle. It's very rare. So maybe in some cases you have that, but you would have it maybe for 100 or 200 videos and not more. That's also not enough to learn an end-to-end trainable model with all this kind of information. And so I guess it's kind of an open question if in 10 years we'll be able to learn these models end-to-end, or if you still need the structured models. But today it seems like, for example, if you look at my third example for the self-driving cars, it seems like completely impossible to do the whole pipeline end-to-end, right? Already now, we're happy that we can do this model, this structured model, but doing the whole pipeline end-to-end is not possible. But who knows? I mean, it's not clear if in a long time away, if you have found a good way to train and a good way to implement things, maybe it's possible to actually maybe do it end to end, having the structured model somewhere in the middle, right? So you could imagine that you have this, like similar to what we're currently trying to do with the transformer. We're trying to have a structured model with the transformer and then training the whole pipeline end to end. But there already it's quite complex in time, right? Because you have to store the whole model plus the features in memory and train the whole thing end to end, and that makes it quite hard.
Yeah, I guess there's both the computational complexity and then the training data, which that makes a lot of sense.
Yeah, it's not clear, right, if it's solvable or not, but I think if we have a good grasp on the tracking, it can help in the near-term future, and maybe it's even necessary in the long-term. And maybe it gives us also a way of finding, like even tracking is not today, not end-to-end, right? This is kind of things which we discussed previously. Can we do the tracking end-to-end? For now, no. And if we had maybe a good way of doing the tracking end-to-end, it could give us an idea how to do the full model end-to-end as well.
Thanks.
Thank you.
All right, well, if there are no other questions, I think people are shy. Yeah, I don't know, Alyosha, Tarasha, if you have any more questions, otherwise we can move on and thank Cordelia.
Yeah, no more questions from my side. So I would like at this point to thank you again, Cordelia. Thank you very much.
Okay, thank you.
Sorry, go ahead.
Yes, you tonight, right?
Yes, so we'll have Cordelia back again for the roundtable. I think it's in 6 hours or something. Don't trust me, just go check the schedule on the website. But later tonight or this afternoon, based on your time zone.
Okay, thank you. Bye.
Thank you.
Thanks so much. All right. Many thanks again to Cordelia. And our next talk is from the winner of this year's Tao Challenge, Fei Du. Fei is a doctoral student at the Harbin Institute of Technology, and he's currently interning at Alibaba. And his team submission this year outperformed our baselines on Tao by a whopping 17 AP. So I'm really excited to hear about his approach. And with that, I'll hand it over to Fei. Fei, are you able to talk and turn on your video?
Is my voice clear?
Yeah, we can hear you.
Yeah.
I promoted Fei to being a panelist, but okay, cool.
Okay. Hello, everyone. I'm glad to show our approach and the results here at the first Training Any Object workshop. We are from Damo Academy, Alibaba Group, except Xu Bo, who is from Cainiao Corporation. I'm Du Fei. First, let's have an overview of the task. The whole dataset contains almost 3,000 videos, which are far more than the popular MOT challenge. There are totally 482 categories in this challenge. Compared to the person or car tracking in MOT challenges, this task is very challenging. Besides, annotation in this task is 1 FPS based, and the number of labeled objects per video is limited to 10. Factors including occlusion and camera motion also make this task challenging. In addition, the evaluation metric is changed from MOTA in MOT challenge to track MAP, which emphasizes on the precision and accuracy of the tracks, not individual detections. We name our method as AOA, which means any object association. The whole pipeline of our approach is surprisingly simple but effective. A solid detection model is first applied to detect the target. Then we extract the appearance features for each detection box and link them to time at 1 FPS. Finally, a post-association model is applied to associate broken trajectories. I will further introduce each model respectively. Since the whole dataset is built with the Elvis label, we choose the method bags from Leal with their best implementation for detecting on such a non-tailed data. The bags groups the categories according to the number of samples and perform softmax within each group. We show the performance of models and trained with and without group softmax. Here, the prefix GS denotes banks. As we can see from the second and third rows, banks significantly improve the detection performance on top. Following experience from the detection community on model ensemble, we train another model with different backbone in order to differentiate from the previous one. This model is also fine-tuned with group softmax. Considering the metric MAP, a trick here is to just output 300 boxes within the 400 categories in top. Compared with over 1,200 categories in Elvis, this can improve the recall of each category. As for the tracking model, we have several options. Since there are many MOT methods in recent years, some end-to-end deep models demonstrate high performance in the MOT challenge. However, as we need to track any object in this task, these deep models cannot be directly used. Besides, we lack enough training data to train a new deep tracking model. Also, most deep model is not efficient enough, and we don't have enough time to do that. So we decided to use simple models like sort and deep sort. Compared to modern deep models, sort and deep sort are efficient at 30 FPS. However, tracking at 30 FPS will find that the sort and deep sort cannot track the target for long time. Then we try to track the target at 1 FPS. As the shape and location of the target changes dramatically, the geometry information is not reliable when tracking at 1 FPS. So we remove the prediction and IOU matching parts of the deep sort and only use the appearance features for target association. In this way, our approach is extremely efficient. However, to accomplish this task, we need a robust category agnostic appearance model. The first appearance model we have tried is an SOT-based model. We use a Siamese network inspired by popular SOT frameworks to learn the target features. The model is built to discriminate the target from distractors. After feature extraction with ResNet 50 backbone, a 256-dimensional feature enters the center point of the feature map is selected to represent the given object. The second idea to train the category agnostic feature representation is borrowed from the person reality community. Training data is collected from SOT domain with over 320,000 IDs. Each trajectory in the original SOT dataset is regarded as one ID. Then we apply general reality training pipeline and tricks to train the appearance model. Let's take a look at the experimental results. First, we can see the results of different tracking models. The tracking results are obtained using the same detection boxes. The 1 FPS based deep sort shows much higher performance compared with the 30 FPS based sort and deep sort. Here we also tested the MPN method, which is a graph neural network proposed in CVPR 2020. It also shows inferior performance compared with our 1 FPS based deep sort. Then we compare different appearance models. Here, SOT and reality stand for the SOT-based and reality-based appearance model, respectively. We can see that the SOT-based appearance model shows inferior performance compared to reality-based one. This situation is more obvious as our detection model getting better. In spite of that, the features from the SOT and reality-based models can be concatenated to obtain better results. So we train two reality-based appearance models. The first one is trained with a big instance level softmax function, and the second one is trained by adding the tau training dataset with softmax and triplet loss functions. Overall, the object is represented by concatenating features from the two reality features. Next, we show the results of using different detection models. Here, the The number 482 denotes that the model only output 482 categories in tau dataset. We can see from the first and second rows, the performance is improved by only output these categories, since the recall is improved. The check oracle results are also shown by directly assigning the per frame detections to ground truth checks. The results show that our detection model sets a much higher upper bound compared with the baseline detection model. Also, we can see the second detection model shows slightly better performance. Finally, I describe our ensemble method and the final results. A common method to combine two detection results is NMS. However, we find that directly concatenating the tracking results of our two detection models demonstrates surprisingly high performance compared to the commonly used NMS. By concatenating the tracking results, the track oracle results is also improved dramatically. Our final results are obtained by a post-association method, which relinks two tracknets using the tracknet level mean appearance features. Here we show a demo of the tracking results. Okay, thank you.
Awesome. Thanks for the great talk, Fei. I'm super excited about this method. Actually, I think this is something that I feel like we've talked about a few times, especially on building Tau, is how do you best incorporate single object tracking training data into a multi-object tracking method. And I think you guys have done that very nicely. I guess we have maybe time for one or two questions. I'll ask one in case anyone asks until someone asks in the chat. One question, so it seems like at 30 FPS, you're actually doing a little bit worse than at 1 FPS. And I'm curious if that's, like intuitively, that seems a little, yeah, it seems a little unintuitive, because I would think, when you have more information, you should always do better. Do you think it's just a matter of it's harder to iterate at 30 FPS, and so you weren't able to kind of tune that model as well, or do you think there's something else going on?
I think tracking at 30 FPS, the tracker is easily to make mistakes. I measured the track length, the length of the tracks of 30 FPS based tracker and 1 FPS based tracker. The deep sort in 30 FPS can only get about the length of the results is about 2. But the length of the 1 FPS based tracker is about 8. Then the oracle results is about 14. So I think the tracker is easy to make mistakes in 30 FPS.
Got it. Thanks.
Yeah, I think I had the exact same question, but I guess as a follow-up, so the deep sort that you use at 30 FPS, does it also have the IOU matching? Because I think you said that you removed the IOU matching.
No, yes, I removed the IOU matching, and the prediction the regional deep sort use the Kalman filter to predict the target. We remove them all, and we only use the appearance features to associate the target.
I see. Okay.
Looks like there's a question in the Q&A.
Yeah.
So the question is, for which type of error is the aggregation of multiple models, NMS or concat, more beneficial? Does it decrease the misdetection rate? Does that make sense, Faye? I think the question is, what is helped the most by aggregating multiple models? Is it, decreasing the number of false positives? Is it increasing the recall, or is it increasing the classification accuracy? Do you happen to?
I think concatenating the in our experiment, concatenating the tracking results of the two detection models get much higher performance. So I think the best benefit comes from the recall. Yes, wait.
Great. All right, so that was answered. All right, I think we don't have any more questions, and we're also, I think, 15 minutes behind on schedule, so we'll move on. Thanks again, Faye, for the great talk and for the great submission.
Thank you.
I might contact you with more questions later on.
Yeah, I'm also super intrigued to know that their approach improved by such a large amount over our baseline.
Yeah, it's really impressive.
So moving on with our schedule for session 1, I am honored to invite our next speaker, Leal Taixé, who is a professor at the Technical University of Munich and leads the Dynamic Vision and Learning Group. Her interests lie particularly in object tracking and segmentation, and she has played a key role in advancing the field of multi-object tracking. Prior to joining TU Munich, Laura spent 2 years as a postdoctoral researcher at ETH Zurich. She is a recipient of the prestigious Sofia Kovalevsky Award and the 2019 Google Faculty Award. Let us all extend a very warm welcome to Laura and listen to her in her pre-recorded talk.
Hello, welcome to my talk. I'm Leal Taixé. I'm a professor at the Technical University in Munich, and today I will be talking about promising research directions in multiple object tracking. So multiple object tracking is the task of tracking all of the objects in a scene. First, detecting them in all frames, and then following them frame by frame, thereby tracking them in a scene. And as you can see, multiple object tracking can be difficult when the camera is moving, when there's a lot of targets in the scene, like for example, in this bottom right scene right there where there's lots of people, they're all moving at the same time. There's also lots of obstacles. So it's in general a very challenging task in computer vision. A common paradigm used in multiple object tracking is the one of tracking by detection, in which the problem is divided into 2 parts. Now, on the first step, what we do is we run a detector on each frame of a video to obtain a set of proposed locations. And as we can see here in the example, a detector is not always perfect, and therefore we might have some false positives and false negatives. Now, these all have to be resolved in the second step, which is the data association step, the one that connects the detections in the temporal domain to create the full trajectories in the video. And of course, whatever error we have in the detection step will be carried over in the data association step. Since 2014, which is when we launched the Mod Challenge benchmark, of which I will talk about later, the community has seen several trends passing by. For example, since 2008, people have been working a lot on data association, on improving this second step of tracking by detection, using more and more complex graphical models. People have also focused on motion models, on learning appearance models with deep learning after 2015, more or less. And finally, there has been a trend of methods that use tracking by regression and that have been recently been pushing the performance of multiple object tracking methods. And so today I will focus on 2 works that we have developed at the lab and that I think have the potential to push the field forward and to really leverage deep learning and go towards end-to-end learning in multiple object tracking. So for this, we will go back to the paradigm of tracking by detection, and we will take a deep look at the detection step and the data association step, and see how can we better leverage these two steps, how can we better solve these two steps, and how can we build up to go towards end-to-end learning. So let's start by taking a look at the detector. Now we will focus on regression-based detectors, like for example, faster CNN. Now these detectors take an input image and create a feature representation of that image with CNN, and then use region proposals to find regions of the images that are potentially interesting, that potentially depict an object of interest that we want to track. Now these region proposals are going to cut this feature representation, right? So only part of the feature representation is going to actually represent that region proposal. And so from this cut feature representation, what faster CNN does is it puts a classification head and a regression head on top. The classification head tells us whether this region proposal depicts a person or a car or any other object of interest, while the regression head corrects the bounding box coordinates in order to better fit this object. And this is where it gets interesting, right? Because how this regression head actually works is it takes a region proposal which is maybe badly placed on top of the object. So it doesn't tightly fit this object. And what the regression head does is it changes the coordinates of this bounding box. It regresses some new coordinates. So then now the bounding box is tightly fit around the object. And now this regression is what is really interesting for us. Because what we thought back in 2019 is, well, this is very similar. This regression step of moving the box is actually very similar to what we want to do in online tracking, right? We want to adapt the box from one frame to the next in order to track an object. And this exact idea is what we use in our paper, our ECCV 2019, to go from a detector to a tractor, which we define as a method that is trained as a detector, but that actually has tracking capabilities. So let me show you how this works. We're at frame T+1. We have already tracked 3 objects throughout the video up until frame T. And so what we can do is we can use the detections, these locations of the 3 objects of frame T, as proposals for frame T+1. So in this case, we're not going to use the region proposal network of faster CNN just yet. So we're going to take these 3 boxes, which we know what pedestrians they represent. So that's why I colored these boxes with 3 colors, because I know the identity of these boxes. And I'm going to use these boxes of frame 3 as proposals for my regression to frame T+1. And my regression head, what it's going to do is it's going to regress these bounding boxes to fit tightly into the new location of these pedestrians at frame T+1. And therefore, now the question is, with this regression step, can I answer the question, where did my detection with ID 1, for example, the red box, where did it go from frame T to frame T+1? Can I answer this question? And the answer is yes, which means that with this regression, what we're actually doing is multiple object tracking. I've been able to track the red pedestrian from one frame to the next. And this is exactly what I used in order to do multiple object tracking. Now, this simple method is very powerful, and of course has advantages and disadvantages. So one clear advantage is that we can reuse extremely well-trained regressions, and so we get automatically well-positioned bounding boxes. Another advantage is that we can train our model on still images because it's trained as a detector. And therefore, we have an easier time at annotating new sequences, new objects. For example, if now I want to go from tracking pedestrians to tracking special cells or special animals, I don't have to label hundreds and hundreds of videos, but I have to label only images, and suddenly I can do detection, and I can also do tracking of these new cells or these new animals. And another advantage is that our method, Tractor, is actually online, so I can use it potentially for real-time applications. Now, of course, there are disadvantages to this simple method of doing multiple object tracking. And the first one is that the model has no notion of identity. So in crowded spaces, it can get easily confused, right? All that the model is doing, which is in the end a fast RCNN model, is taking a box and snapping it to the location that is close by and that resembles an object of interest, in this case, a person. If this is the same person that was in the box at frame T or not, this is not something that this model is going to judge. Therefore, it has no notion of identity. Now, the other disadvantage is that, as any online tracker, the track is going to be killed if a target becomes occluded. Therefore, we need a method to close small gaps and occlusions. Now, for both of these disadvantages, what we can use is a re-identification model. Now, there is a huge literature on re-ID, and therefore we can take one of the methods of re-identification and apply it here in order to solve both of these problems. And what re-ID is going to do is it's going to take two bounding boxes and it's going to judge whether these two boxes represent the same person or not. Now, a third disadvantage that we have to deal with is that the regressor only shifts the box by a small quantity, right? This is faster CNN, and therefore the bounding box regression is only to slightly correct the position of the box. And therefore we cannot deal with large camera motions or large displacements of the pedestrians due to low frame rate. Now, in order to solve this particular problem and help with the second disadvantage that is mentioned on this slide, we can actually use a motion model, either a camera motion compensation or, for example, a constant velocity model for pedestrians in order to predict where the box is going to be and then regress the box with the regression head of faster CNN. Now, these two changes are very important to bring forward the performance of Tractor. So we can see here three measures. The first measure, MOTA, is the measure of accuracy that we use in the Mod Challenge benchmark and that is widely used in the community to measure the accuracy of multiple object tracking methods. And we can see how this accuracy is increased if we use re-identification and a camera motion compensation. But the measure that is really increased is the measure IDF1, which measures how much are we keeping the identity of a trajectory. Are we performing a lot of identity switches? So in this third column, we show the identity switches that we do. These are the errors in preserving the identity. And we see that with re-identification and a motion model, the identity switches are heavily reduced. So we have this simple baseline of Tractor, which essentially takes a detector and gives it tracking capabilities. And then we have the re-identification and motion model, in particular camera motion compensation, in order to boost the results even further. And with this very simple method, we get actually state-of-the-art results. And so the question that we also wanted to solve in this paper was, what are all the other methods doing? So there has been a vast literature in multiple object tracking. So how come such a simple baseline is beating all the other methods? And so we started looking into the results. And so what we're plotting here is the bounding box visibility on the x-axis and the percentage of tracked bounding boxes in the y-axis. So these are all of these columns that you can see here. These are different methods. And of course, as the bounding box visibility increases, almost all the methods are able to track these really well visible bounding boxes. Now these bars on the background are the distribution of occurrences in the ground truth. And as you can see here, most of the boxes are have a high visibility. So most of the boxes are almost 100% visible, which means that the tracking problem is very, very easy for most of the boxes. Now, the other extreme happens here, where the boxes are completely occluded. And in the middle, we don't have so many examples of boxes that go from a visibility of 0.1 to a visibility of 0.9. This might explain why the MOTA is so hard to change, even though methods keep improving results, because for most of the cases, it's either very simple to track the objects or extremely hard because they are not visible at all. And so the first thing that we want to do is we want to compare our method with and without this re-ID and the camera motion compensation with some methods that use, for example, graphical models or online methods. So we have taken these 4 methods, some of the state-of-the-art up until the time, and what we want to do is we want to compare their performance with our method, and we want to see how does each method perform when we change the bounding box visibility. So as we can see, in this middle range is when our method really shines. So from bounding box visibility of 20% to bounding box visibility of 70% is where our method really outperforms all the other methods who really suffer as the bounding box visibility decreases. And so this seems rather counterintuitive, right? Because some of the other methods are methods that employ graphical models that look at the past frames, at the future frames, and try to make a decision over all frames. So one would think that they can actually fill in the gaps, right? Interpolate these positions in the frames where perhaps the object is not really 100% visible. But it turns out that those methods are more conservative, and so what they decide to do is often they decide to stop tracking an object because otherwise one would create easily false trajectories, ghost trajectories. And therefore this means that our method in this range is the only one that can actually track the objects when the visibility goes down to 20%. So it's interesting to see that none of the tracking by detection graph methods are more capable of recovering the trajectory in these scenarios where we have partial occlusions. This seems very counterintuitive, and it also seems the kind of scenarios where we cannot rely on detections, and therefore tracking should really step in. All tracking methods should really step in. But what we're seeing here is that this is not really the case. So what we learned from this analysis is that the hard problems in tracking are still unsolved. So we're not able to cover large gaps in detections due to partial occlusions or due to other problems, illumination problems, for example. Many methods can also not recover from partial occlusions. And there's, of course, another problem of tracking small targets, because there we have very, very few detections, because detecting small targets is extremely hard. And therefore, if we don't have any detections, we also cannot recover any of those trajectories. And so what we figure out after presenting this baseline, after transforming a detector into a tractor and getting state-of-the-art results, is that all of the other methods, instead of targeting the real problems in tracking, they're just marginally improving on what we call the easy scenes. Those scenes where the pedestrians are mostly visible and where you just need to recover from 1 frame or 2 frame gaps where maybe a detection is not really available. And in fact, we saw that the accuracy in tracking has only increased by 2.4 percentage points in the last 2 years of the Mod 16 challenge, in Mod Challenge. And therefore, in 2 years, we have really just marginally improved on these easy scenes, and we left all of these hard problems in tracking actually unsolved. And so moving forward, what we propose to do is we propose to handle those easy scenes, those small occlusions, with Tractor. So we can use a detector for much more than just applying it in each frame of the video independently. We can actually use it to perform tracking and to solve all of these easy scenes. If we put on top basic ReID and a motion model, then we get state-of-the-art results. So we are absolutely sure that a detector can be used for much more when it's used as a tractor. And so now what the community should be doing, should be focusing on, is focusing on harder cases, focusing on the long occlusions and focusing on extremely crowded scenes where tractor can get easily confused. And this is what we're going to focus on this second work that I'm going to present today. So we're going to take another look at the data association step. And in particular, we will look at how data association can be formulated as a graph problem. So this is a formulation that was presented all the way back in 2008. And what this paper proposed was to consider the mod problem in view of a graph, in which the nodes represented detections and the edges represented connections between those detections. And so active connections between one detection and the other would mean that these two boxes represent the same person, and therefore they form a trajectory. So by solving a clustering problem in this graph, one could obtain the trajectories in the video. Now, in order to solve this problem, we still need to extract features from the image and embed them into this graph. We need to tell the network that 2 images are similar or 2 images are not similar and therefore represent different people, right? We need to bring the features from the image and embed them to the graph. And so in this classic view of things, what one would do is it would extract features, handcrafted or deep learning features, appearance features, and it would embed them into this graph. Now, on top of this, we would have, for example, a discrete optimization algorithm that would optimize the full graph and obtain the trajectories based on the features that we have extracted from the images. Now, the main problem here is in the feature extraction step. So one needs to define costs for each of these edges, and the costs roughly state how similar 2 images are or how dissimilar they are. And so if we take, for example, these 2 images, what we can do is we can embed them with any other features, spatial temporal cues, and we can put everything into a neural network that would map these 2 images into a cost for the edge. And so this cost is going to tell us how difficult is it going to be for my optimization method to link these 2 nodes and therefore to create a trajectory. And so, of course, if we have the 2 images in different frames that are depicting the same person, the neural network is going to assign a lower cost into this edge, while if we have different persons, like is the case here at the top, the neural network is going to assign a higher cost. And so this is one way where we can obtain rather robust appearance models, and we can use neural networks to extract these features from the images and embed them into the graph. Now, the main problem with this approach is that the feature extraction and the discrete optimization are still two different processes. So the feature extraction has no idea what the discrete optimization is going to do, and the discrete optimization has no power to change the features, just has the power to solve the problem with the features given. And so what we wanted to do was to use a neural solver that would go directly from images to the trajectories and would do both steps at the same time. It would do the feature extraction step, and it would take into account the domain in which this feature extraction is supposed to happen, which is the graph domain. So we want to implicitly encode high-order information. We want to learn to perform data association, and at the same time avoid the need of this expensive discrete optimization, which can actually take sometimes days to solve a problem if we're talking about quadratic programs. And so this is what we propose in this CVPR 2020 paper. So we're going to use the graph view of multiple object tracking. And we're going to construct this graph in which the appearance of each person, of each detection, is going to be encoded by a small CNN, and it's going to be encoded in the node representation. Now we're going to use neural message passing networks in order to let all the nodes communicate with each other and see, what is around, what is in the neighboring node, does this node look similar to me or not? And this communication is going to happen on the graph domain. So the domain of the problem is where the feature learning is going to happen. After this neural message passing, we're going to perform edge classification, which will tell us whether an edge is active or not, and this will allow us to recover the trajectories. And so we can see that these two steps, the feature extraction and the data association, are now no longer separate, but one can actually backpropagate from the edge classification all the way to the feature extraction to the image. Now, for computational purposes, we're not going to backpropagate all the way to the image, but this is in theory very much possible. So the cool thing about this is that we can directly work in the multiple object tracking domain by using message passing networks. And so the learning, what it's going to do is going to take into account directly the structure of the problem. And therefore, the features are going to be much more powerful and targeted specifically for the mod domain. Now, in this work, the key technique that we're going to leverage are message passing networks. And so these are networks that take as input a graph with some node features and also edge features, right? Some feature representation that can come from a CNN, or it can be just handcrafted features that represent, for example, the distance between these two bounding boxes. And now the interesting part is going to happen here in the middle. This is where the message passing is going to take place. And essentially what the message passing does is it propagates the information across the graph for several iterations. And for each iteration of information propagation, we can actually view it as one layer in a neural network. So one propagation of information, one step of propagation is going to correspond to a hidden layer in a neural network. And now in the output, what do we have? We have a graph, the same graph, but now the node and edge features have been updated. And they have been updated with information about the neighbors. So they are aware of their context, of what kind of detections are around them, and so who is going to be similar and who is going to be dissimilar. And so very briefly, message passing networks, how the learning process goes, how this information propagation is actually taking place, is in two separate steps. In the first step, we have the node to edge update, in which the nodes pass information to the edge, and so the edge embeddings, you can think about the edge embeddings as this vector that is being updated with the information of the nodes. And in a second step, we have the edge to node updates, in which the edges pass information to the nodes, and now it's the turn of the node embeddings to be updated. And so if you want to know more about message passing networks for multiple object tracking, I've left a link for you down here where you can watch a video with a bit more detail on how message passing networks work. And so by repeating these two updates for a fixed number of iterations, which are called message passing steps, we're going to encode this context into the node and edge embeddings. So the node and edge embeddings are going to become much richer of information that is coming from the neighboring nodes and the neighboring edges. And so this is essentially what is happening during this information propagation. We're just updating these embeddings. And now these embeddings are going to be much more useful for our task of classifying the edges into active and non-active edges. And so again, what neural message passing does, it is going to propagate this appearance and geometry information across the entire graph. So we're going to obtain our new embeddings that have this high order information, right? All the detections, depending on how many message passing steps we do, have received information from far away detections, and therefore they have an idea of this higher ordered information. They can look into the future and they can look into the past frames, and they know what kind of detections are out there in future and past frames. And so now once these embeddings have been updated and now they encode this higher order information, now we're ready to feed these embeddings to an MLP and predict whether an edge is active or not. And again, this edge now contains extremely informative, higher order information about the graph structure. It's not only looking at its own, detection on the left, detection on the right, but it has much more information about what is happening around, what is happening in past frames and future frames. And therefore, a simple MLP is going to be able to predict whether an edge is active or not active. And so these edge predictions that we obtain with the sigmoid, we obtain them at iteration L, which means after L message passing steps. We have also weight to balance active and inactive edges, because we have the problem, of course, that most of the edges are inactive, so we have to take this into account in our loss function. And another key insight of the loss function is that we're not going to compute the loss only at step L once we have performed L message passing steps, but we're going to sum up the loss over the last steps, like for example, over the last 4 message passing steps, so that the network can learn much better embeddings this way. Now, the first thing that we're going to look at in terms of results is going to be what is our accuracy as we increase the number of message passing steps, right? Is it really useful to perform so many message passing steps? Well, it turns out that going from 0 to 2 message passing steps boosts the accuracy, the MOTA, by quite a lot. Because 2 message passing steps is when we start collecting higher order information from neighboring nodes. Now, after that, the performance increases just a little bit, and in our case, it reaches the peak at 12 message passing steps. So we can see here how this collection of higher order information really boosts the performance of MOTA and IDF1. Now, even though this gives state-of-the-art results in multiple object tracking, there is still a lot of things that we can do with message passing networks. And I think this is a great first step towards end-to-end learning for mod. But there's still a few things that we're not doing right. So the question is, can we, for example, embed into this graph formulation the detection step? For now, this is still a separate step. We need to decide which detections we're going to put in the graph or not. Can we embed this into the graph formulation to have truly end-to-end learning? Can we leverage the tractor paradigm? We've seen that it works really well for these easy cases. So can we embed it inside the message passing network? And finally, long occlusions, when the pedestrian is going, for example, behind a tree or behind a crowd of people, this is still a problem which is not totally solved even with message passing networks. So we need to do a lot of work on trajectory prediction in order to solve these long occlusions. With this, I conclude my talk. I would like to thank my students, Guillaume and Tim, who have been working on these projects, and I thank you for your attention.
I think that was a very encouraging insight into end-to-end learning for multiple object tracking. So we did answer some questions here that were asked for Laura unofficially, but I think it will be good to move on to our next speaker because we are 10 minutes over schedule. And if you still have questions for Laura, you can keep posting them in Q&A and we'll try to answer.
Yeah, so this is also what I wanted to say here. I think we should continue, and then after these talks, we can just keep this session going, and we can answer more questions. And now, we should move to the next talk. And here I actually have a great pleasure to announce that our next speaker is Jiri Matas. And Jiri is a professor at the Technical University in Prague at the Center for Machine Perception. His research focuses on computer vision, recognition, machine learning, and sequential decision making. So Jiri received several Best Paper awards and has co-authored several patents. And he also supervised projects for a number of high-tech companies, such as, for example, Toyota, Hitachi, Boeing, and Samsung. Jiri is also a co-founder of AIDA Recognition, which is the first spin-off company at the Technical University in Prague. Jiri, we are really looking forward to your talk. Thank you very much for coming here, and the stage is yours.
Okay, so thank you for the introduction. Let me just share the screen with you.
Regarding that, can you tick these options at the bottom before sharing screen? They're called, just a second.
So I think I'm sharing the screen.
Okay, so let's just continue, and if there will be any troubles, we can restart the screen sharing. Usually there are two options that should be ticked: share computer sounds and optimize screen for sharing.
Okay, so can you see my screen?
Yes.
Okay, so hello to everybody to this workshop, which has started with nice talks. I will give a fast overview of my talk. So I will first talk about the zoo of tracking problems, so different types and categorization. Then I'll switch to visual object tracking challenge, which is a very long running object challenge benchmark, which tries to evaluate short and long-term single object trackers, and has run for some time. That I think it has shaped the field, and I will share some insights from, or maybe the philosophy of how we run the things, so that it's very useful for the community. Then I'll to give you an example what would be a typical entry into the visual object tracking challenge, because people notice what performs well and they copy from each other. So I will use a method D3S that with Alan Lukasic and Matej Kristan we developed. And then I will make a few maybe contentious predictions and conjectures about the future of tracking and maybe convergence of related fields. So there, this might be a good starting point for the discussion later on, maybe in the evening. So I think that two main branches of tracking, and this is true for video analysis, are those which see the tracking as correspondence search and those that see the segmentation. And I think recently there has been a huge progress in the segmentation part. Maybe because it's perhaps easier to get representation of the segmentation. This is just a region. Whereas in the correspondence search, if we move from a 2D world, which is the one maybe visualized in the top frame here, it's very difficult to speak about correspondences, especially in 3D, 6D, because we need to have a generic model of the surface that we are observing or tracking, and that's quite difficult. Even optic flow methods are, I would say, cannot handle such generic scenes as tracking by segmentation. So sometimes applications require the correspondence, sometimes the segmentation. Sometimes the applications would really require more, or the method itself. So you might want to track an object and at the same time build a 3D model. For instance, if you want to understand the 6D pose. So for robotic manipulation, you can't really view the object as a 2D entity that is just to be segmented. You need to know something about its 3D structure to speak about rotation and translation. And towards that end, we propose one of the first methods with Kart, Lukacic, Kamerainen, and Kristan at CVPR20, but this is a very open problem. And so far, nobody talked in this workshop about SLAM. So SLAM is sort of a misleading name somehow, but the people who study SLAM have been quite successful in building 3D models of the environment and the position of the camera with respect to that environment. So they were tracking the camera. But now they realize that often the scene is not rigid. Different objects move in the scene, and they start to talk about partial SLAM or multi-body SLAM. And multi-body SLAM is actually tracking all these things with 3D reconstruction. So I see there will be a convergence among the SLAM domain, again, a quite separate community, like the multi-object, like the single object tracking, that hopefully will converge. The classical 6D pose tracking problems, as visualized here on the face, are often supported by a very strong prior model about the object to be tracked. So maybe now open pose, you can say it can do miracles, but that's for a very particular class of objects, human bodies. Fine. And this now connects me to the TAO workshop. I see quite different problems when we are tracking an object or something that can be called an object, like a butterfly, a rabbit here, a human, a runner. And if we are tracking an arbitrary region. So, okay, in this particular example on the left, we are tracking a deer's head, but we could have been tracking just the ear, maybe to do some augmented reality on it, or maybe we could have been tracking the front leg because we want to study whether it's limping. So it's not clear that a lot of arbitrary region target tracking, it's so easy to use a lot of learning a priori. So it seems that the previous speakers, they really thought about object tracking and multi-object tracking rather than multiple target tracking. And you might, like here we are tracking the invisible white rabbit, nearly invisible, but we might have been tracking some lump of snow in this avalanche. And that's also something which is trackable, for instance, to estimate the speed of the avalanche, volume moved per second, and so on. And maybe these two will split the vision field rather than the current split between, say, video segmentation and tracking, but maybe this might be a fundamental split between arbitrary region tracking and tracking of entities which are objects, instances of known classes. Another distinction, which I think will converge with the short-term trackers, is long-term tracking, which goes back, maybe I think the paper TLD I co-authored in 2010 is one of the first to speak about long-term tracking. And it's related to what Laura was speaking a little bit about. Sometimes the target disappears from the field of view. Sometimes it gets fully occluded. And sometimes it's impossible to distinguish. So regardless of how well the visual model is designed, the short tracker will fail, which means in some data associations will not happen in consecutive frames, and you will have to re-recognize. So even for arbitrary targets, we need to do some association between frames which are not adjacent. And then if long-term tracking can build a detector, then we are very close to this combination of object detection and association and tracking based on properties in the current sequence. So this is an example, really, like this is a ancient video by these standards, maybe 8 years old or 10 years old, 8 years. And it shows that short-term trackers fail on the first occlusion. And really what you should be doing partially when you are tracking the panda is build the model to redetect the panda. So if I move somewhere forward, the panda disappears, and later on it reappears after a short toilet break somewhere at the bottom. And you see it's the end of the break. And panda comes back and it's redetection. So although we didn't have a model of the panda, we could redetect it because we could build it. It was a long-term tracker. So I think if there's a convergence between long-term tracking and short-term tracking, there might be convergence between multi-object tracking and tracking, the generic tracking. When we talked about the full range of problems, these days biologists would like to track in a multi-cell organism the evolution of every single cell and splitting. So maybe the generality of what we think about, at the beginning people are saying we need diverse training sets. By the diversity of things that have to be tracked is well beyond using 400 classes. We don't have methods, or very few people. I haven't seen a paper which would model splitting events in a tracking paper. This is from paper. This is super ancient paper from these 2006. Sometimes it's still worth talking about papers from that era. And it was an extremely important, impressive paper by Helmut Grabner, who was able to track something transparent. How could that be done? You realize that, of course, the signal inside the glass is changing. You can't do that. And what they were showing a box around the glass, but actually they are tracking the hand. So what's going on here? Well, you are tracking some sort of related companions, and that allows you to track the invisible. So this might be what, if you talk about graphs and related things, if a classical tracker would be asked, show me where the Red Bull can is, it will be in a problem now because it's fully occluded. If you ask people to mark it, well, they might slightly disagree. These are positions given by a number of students in different colors. You see that they spread out, but roughly it's doable. And so if you are tracking, you might be actually modeling the environment, how things, so this would be a classical tracker lost. But a tracker which says, aha, the object I'm interested in is correlated in its motion with many other objects, or not objects, but regions. Actually, you don't have the concept of object. That's a very high level concept. We are tracking a point here, and we associate it with some other entities in the sequence. So it's possible that full modeling might require even bottom-up build-up of this type of companions. They don't have to be only in terms of objects. To me, the world where we are operating with known objects is fairly restricted, and it's sort of an object. It's a world in which we face familiar entities. Just another exotic thing. Imagine that you try to do multi-object tracking on table tennis sequences where the ball looks like this blurred long streak. The same thing with the tennis ball, the same with the flies. In the right bottom, or maybe bees, the bottom right long streak is actually a fly. So I think that the richness of the world is really much bigger than most people in their research consider. And we are moving a lot in that direction. We started from 1 image to 10 images to 10,000 images, well, to 1,000 images of 1,000 classes. Huge progress in, say, with ImageNet, but still, to go general requires a long-term effort. So this has been touched before. There are many applications of visual tracking, and some require correspondence, some segmentation, some both. So I think that progress in both is really required. And it seems to me that the correspondence is quite common, or both, like in, say, in sports. Okay, fine. you might like to have segmentation to have rough position of the sportsman, but to do any reasonable analysis, you have to have understanding of where particular joints are and what the changes are, and that requires correspondence. Fine, if it's a specific class like pose of objects, we can do this now. But if we want to do this general, now we would like to do it for analysis of runs of different animals. It will require a lot of work. So in some cases, robotics will need both segmentation and correspondence. So both problems are important, and my feeling is that the segmentation problem has progressed much faster. So now I'll switch to the visual object tracking challenge, which we have been running since 2013 with a group of people, with a committee, and that the effort actually tries to standardize the data sets, which is one of the, let's say, critical parts, have evaluation systems that push methods in the right direction, because this is a common thing. You realize you have an evaluation metric which can be gamed, and weird things start happening. The fastest trackers take 1 hour to process a frame. That obviously is not something that an application is waiting for. And of course, provide tools. So I'll just give a brief, okay, the committee is now a fairly large group of people because we are, a lot of work is involved. And I will just speak now about our objectives and our approach, which might be slightly different from what you've heard before. So we would like to make the benchmark useful for the community. So people in the community want to know which method works best, which method should I read about, which methods I should build on. If I have an application, which method I should use, but also the authors. We want to give them fast feedback on design choices, which also means we would like it to be very easy for the authors to submit their code to the benchmark. We see the efficient evaluation as an important property. So, and we've done experiments which show that meaningful evaluation does not need to happen on a very large data set. I think this is a very important point. So people now race for the largest data set. If you do training, yes, larger data set improves your method, but for evaluation, you don't have to do that. If we are examining a person in maths, you don't have to give him 10,000 examples to see where they are. Maybe you want a stage like simple sequence, more challenging, and so on. You need diversity. So we have tried to maximize the diversity. And efficient evaluation, besides making it our contribution to global warming, because the energy you waste on GPU running 80 submissions on 10,000 sequences, 5 times to get rid of randomness, that really takes time and actually it costs some money. We see that efficiency of evaluation is an important thing. Now, maximizing diversity, what we try to do, we actually do automatically things. When results on some sequences are highly correlated, one of the sequences is redundant, we try to replace it. We try to borrow from anyone else. Okay, 5 years back, there was a workshop on biological tracking in biological data. Okay, we have a sequence about tracking ants. So now, last year, there was a sequence, a workshop on tracking from UAVs. UAVs have like very unstable cameras. Okay, we insert a UAV. So of those, there's like how many? 90 people listening to this. So if you think that you have a sequence which is not at all represented well in the VOT data set, please come forward. And we try to have a compromise between backward compatibility and evolution. So lots of papers are using old benchmarks, which are sort of saturated and old methodology. Of course, there is always a trade-off, but if you slowly move your methodology, you are pushing the methods in the right way. We are also trying to find a balance between self-evaluation and independent assessment on sequestered data. So if you have some sequestered data, data which are not available, the ground truth is not available to users, they can't pick, it's very difficult for them to get feedback from it. So we say, well, you do your self-evaluation, you get your feedback, but if your performance on sequestered data is very different, you have overfit, and this will be even made public during the BOT workshop. So also there is some sort of trade-off between information gained from the whole exercise and complexity. So going for the largest data set, most complex setup is not what we try. You can look yourself, click on the, if you see BOT, this short-term tracking data set. Of course, still there are people, there are animals, there are sports, there are actually multiple animals, so some distractors which are very similar. Any feedback welcome. Because we provide quite precise annotation, we don't rush to change things, but we steadily work on it every year. Okay, so we are using 60 sequences for the public part, 60 for the sequestered, and we do, all frames are manually checked. So we think that precise annotation on a small number of sequences is very important. We do also some extra work. You see that from last year, we have decided that bounding boxes are the thing of the past. And if someone wants a bounding box as an approximate segmentation, say, well, you can fit the bounding box into the segmentation, but it's sort of easy if you have the bounding box, put in some segmentation method. Actually requiring a segmentation is fine. And you see that some of the results we will see are quite competitive to what visual object segmentation people are doing. We are switching from MATLAB to Python, and we are really trying hard so that it's very simple for users to plug in. And the number of entries are high, so I think it's well accepted. Okay. Just about the winning protocol, we realized that we can't really rerun all those entries ourselves. So we try to, we select the top performance in the main measure, and then we run those on the sequester. We run that code on sequester data set. So, okay, it can't lead to some bad results because usually out of the 5 top performance, 3 to 4 perform equally well on the sequester data set. So there's no good to get yourself in the top 5 by overfitting, only to be seen as to drop significantly. Okay, I can't tell you much more, okay, about the results, but one more thing, since in 2017, we saw that people were running methods which took extremely long just to get a tiny margin and to win. So we introduced a real-time challenge where we say, okay, you have to run on some standard hardware at least at 20 FPS. And since then, actually, the leading methods are now near real-time. And maybe we'll drop the real-time challenge because it sort of like became the standard. So at the beginning, people are starting to face a trade-off, but over time, it might be that the best method will be long-term. It will be very fast, and it will be performing almost the best in all circumstances. So we don't have to have like 17 categories of real-time, I don't know, using GPU, short-term, long-term, and so on. Okay, so we have introduced a long-term challenge where the evaluation is different, which is closer to detection, and there's very important to know whether the target has been lost or disappeared, where it's visible. So in classical tracking, usually you give position, and here we say, well, you have to know whether you don't see the object. So the long-term sequences with disappearances are a little bit more difficult to come by, and we are a little bit behind in the diversity here and in the annotation, but okay, any long-term sequences with nice annotations in domains that we have not touched are welcome. So I can't tell you what the results are. The only thing is I can invite you to the Visual Object Tracking Challenge workshop, which will happen on Friday. You see the times, you can find it on the ECCV website. And I guess that some of you should be interested. If you're interested in TAO, you should also be interested in BOT, although of course, the scope is narrower. Now, so how does the state of the art And we picked one paper because I have the material. It's a paper I co-authored. What is the structure of a classical short-term tracker that would be somewhere close to the top? So for a long time, very good performance was achieved by methods based on on discriminative correlation on learned templates, either offline or online, or both, where mainly Daniel's work was exceptional, and that correlation filters would do the search, and they would run on deep features mainly on deep features extracted in some search region. So the challenges to template-based trackers, which operate only on a bounding box, are things like aspect change, because that has to be somehow, the translation is solved very efficiently in the discriminative correlation filters on these deep representations. But if it comes to rotated bounding boxes and change of aspect, they struggle. And it's like some time back, we saw these very beautiful images from the video object segmentation people, but usually these sequences are quite short. They are looking at one object which is very large and in the center. It cannot address significant appearance changes. And these methods used to be computationally intensive. So we thought, well, okay, let's connect the best of the two, make segmentation requirement in the VOT challenge, and let's have a look how this can be connected to the trackers that have been popular there. So this D3S tracker is combining two modules. It's based on some of the atom-like trackers, but there are two structures which are new here. One is like geometrically constrained Euclidean model, which says, well, the structure of the target cannot change geometrically too much, but then there's a geometric invariant model, which can handle significant deformations, and somehow you can think about it as highly improved in terms of representation, something close to histograms. It's not histograms, it's based on samples of the deep representations derived from the object and the neighborhood, but it does not have these geometric constraints. And these two things, it turns out, first of all, they collaborate well, and the representation also facilitates segmentation. It's like the discriminative correlation filter gets some sort of estimate of the current location. You see the response in the middle. So this is like the robust part, which says, well, if there are large translational motions, that's what you should detect. And then this gives some sort of a prior around which segmentation is obtained, and all of that is then fed back. So we have samples from the background, samples from the foreground, and this gives some probability scores which are combined to the posterior. So we have some sort of like probability based, one would say in the old days, this is pixel based posterior, but of course these features have some large receptive fields. So these are quite complicated descriptors which have possibly quite large support. And in the end, you see that the geometric part gives you a location information, but doesn't know anything about the shape of the region, aspect, and scale. And the part which is based on appearance, the geometric invariant one, has problems in distinguishing between repeated multiple objects. But if you put them together, you get quite nice results, some of which I can show. So I will show. The training was on 3,000 videos. Nothing essentially massive. So here we see the result on the butterfly sequence. So the segmentation is near perfect. What is interesting that the tracker was run on the video segmentation data from Davis, and the results are quite nice. So this means although we can handle the smaller objects for the single object tracking, the table here shows that, okay, it's not the best, but it's like among those the methods published until like last year, it was very competitive. So it means single object trackers can now get close to video segmentation performance. Some examples, when you watch this ice skater, one has to be careful that things that look impressive might not be so difficult in the end, and things which are difficult don't look impressive. Perhaps here the background and foreground distributions of deep features are so different that the geometrically invariant module has quite easy life. This thing with the gymnast, again, of course, we know nothing in this approach. You don't know whether this is an animal or a human person. This is general tracking, not using, okay, of course, prior knowledge about the world comes in the deep features, which are trained to distinguish foreground from background, but there is nothing specific for people or any other class of objects. So it's like class agnostic. Okay, so this is an example that you can run it on parts of objects. Now, here is a good example why perhaps tracking by segmentation is progressing faster than tracking with correspondence. I think computer vision doesn't have a generally accepted model for this type of surfaces of 3D objects. So it's very difficult to extract representation from the sequence if you don't even know what it is. So segment, yes, but, and it's very complicated to semi-transparent as the octopus or squid. Now, you could run a single object target without much changes on multiple objects in a video. And for this zebrafish, it works well. For the ants, by the way, this is not multi-object tracking. This is just single object tracking, and even not even long-term. So you don't try to build a redetector. So still, the performance is quite decent. So we tried, and of course, multi-object tracking is not at all solved, but by this, you can see that as soon as it gets occlusion, the segmentation has problems because this is what happens if you run these things independently. But I see there a promise. Things are sort of, I would say, as I said, around the corner. So I will just finish the talk with a couple of conjectures and maybe issues and open problems. So I think that tracking and video object segmentations will converge very fast and impressive performance on general targets around the corner. So really general, like if you, from octopus to a UAV. I believe, for which I have less evidence, that long-term and short-term tracking methods will converge, which means that, what I mean by that, long-term tracking methods, which are those which build the model of an object, will become state-of-the-art for short-term tracking. So you will be able to including redetection on a build model will be helpful. Real-time is not a problem anymore on hardware that can run deep networks. So the dichotomy between good but slow and real-time but bad is disappearing. I believe that multi-object tracking might be solved by multiple single target trackers, and with the long-term trackers which build the model of the identity, and the association problem will be replaced by conflict resolution. So if you think about what Laura was saying a few minutes back, all these message passings are sort of conflict resolution that if multiple objects get together and before I saw them separate, I know that something has to be done and I cannot treat these things independently. Maybe challenging an open problem. I see as the biggest open problem a general, which means arbitrary target tracking with shape modeling. So some targets are articulated, non-rigid, and it requires a generic representation of shape and surfaces that would be perhaps used in many domains of computer vision. So for instance, if you do 3D reconstruction in SFM, people would like to do point clouds, but you don't want to, with a point cloud, it's still not possible to track. In some other places, you have surface representation. So this inhibits the ability to create a 3D model, inhibits the possibility to general track with 6D pose estimation, rotation and estimation, and translation estimation. Same with tracking with dense correspondences. So this video was taken by my postdoc sort of 10 years ago, yes, maybe 7. What we said, okay, look, what we would like to do is to take this object, which is actually hollow, and this type of translation that he's showing now is nothing. But now let's try to rotate and come back. And what you would like to know, that you would like to understand that you came back to the same surface, and that this object is like a triangle, hollow triangular prism, and that you understand that this is rotating. And I haven't seen papers that would be able to take such a video, make the 3D model, and understand in 3D what is happening. And this is maybe my penultimate slide. I would say that the central problem in tracking is conditioning all prior knowledge to the process seen. So if we've seen a person and we have a detector, we've seen all people in all possible conditions, but now we are processing a particular sequence, particular instance of that object, and particular, say, illumination. Maybe in a second, so I think this is the central problem. How much can we rely on prior knowledge? And of course, if we are tracking objects, we can have quite heavy machinery coming, and tracking by detection becomes quite competitive. But okay, is it realistic to have, I don't know, a tracker for a falling rock, something like that? So the second distinction might be between this causal and non-causal. So classical tracking implies causal processing. If I want to track to avoid a car, which is maybe a tire that is lying on the road, I have to make that decision before I reach that. But in computer vision, a lot of tracking is actually, the tracking is the cameraman, and we do just the residual. So it's actually some post-processing. So the same thing, remove something in a video, do content analysis. And maybe this causal and non-causal will have different state-of-the-art methods that if you can come back and process the whole volume, you will get that results. And okay, this is already, we talked about this, that this category or object from a category and target might be an essential distinguishing property of a method. Okay, so just before we finish, we'll start. I have to finish with this thing from a CVPR 94 paper. This is barely 26 years back, and these guys start the paper by saying, although tracking is by large solved problem. So we are sort of dealing 26 years later about talking about a solved problem, but maybe I'm saying this, that one has to be very, it's to put all my claims, conjectures into perspective. This is my best guess, but life could be very different. And thank you, and I'm happy to answer questions.
Thank you very much, Jiri, for this great talk. And I think that there were several very valuable lessons there for our community. So I feel like I learned a lot during your talk.
So surely I'll be in the panel, so people can prepare questions for the panel if we are short on time, which we are. And but okay, I can also answer things on the chat. I'll be sitting here. So okay.
So if it's all right with you, I see that we have here one question from the audience. So
okay,
I'll forward that to you. So question goes like this. For tracking transparent objects, has thought been given to objects that may be related by some phenomenon but not physically connected? For example, a glass and a pen being blown away by a gust of wind, they aren't connected but still connected latently. In what caused their movement?
Yeah, sure, of course, of course. This is exactly that part of the talk where I talked about this companion. Let's say a classical example. You have something, a shadow, so something, for instance, in the early days of tracking cars, it turned out that in California, the trackers work much better than in Europe because it's sunny all the time and the shadow is a feature which is extremely easy to track. So shadow would be something which is related, yeah? So the thing that, when I was showing this example, okay, I can go to slide 9 or 10. And this is an example where the bottle and the hand become connected. If you have a flow of cars, implicitly these are connected. If you have an explosion of someone, I don't know, kicks into 3 bottles, their motion is related. So yes, this is often the case. Or the wind blows 3 leaves of paper. So we don't have many examples of things like that in data sets. Maybe this is the way to, we solve problems which become in the data sets. So we should put into data sets. It's a phenomenon that has been noticed, like in this tracking the invisible. It has many guises, and for some objects, like for instance, it's known that in baseball and things, sports like that, you don't track the ball, you track the movement of the baseball pitcher. So to be fast enough. So it's maybe more common in very fast scenarios than we think. That we know that things are related, cause and consequence, and maybe we should introduce this into data sets where you can't really track easily the object or the target. You have to track use all the information which is related to the event and the motion.
Yeah, this is actually also quite interesting because we discussed that single object tracking should have in the future big impact on multi-object tracking, and actually it's already having now. But that also means it's the other way around, right? By tracking multiple objects, understanding how they move and how they are related to some potential target of interest, this should also benefit the.
Yeah, I agree completely, and it's not like. In some works, I think it doesn't have to be at the level of objects. Yeah, you see some changes in the scene, and you don't have to. You might see, I don't know, something happens. Okay, there is a relationship between objects, but there are also things like stuff. Yeah, you see that a skier, which might be an object, throws a lot of snow from his skis, and you know he's braking or he's turning. Yeah, so I wouldn't say the snow which comes off his skis is an object, but it's some phenomenon related to his motion. And if you understand that, your prediction of where he's going will be better. Okay.
Yeah. Thank you. Do we have some more questions from audience or panelists?
I have lots of questions, but I think I should save them for the roundtable because I think they're more discussion questions. But that was a really interesting talk. In particular, one thing that stood out to me was even in Tau, one of the hard cases we had for labeling were things where you have these instructional videos where people take apart an object, and this is really hard to label, and we don't really have, we haven't figured out how to label these things. We haven't figured out how to build methods for these things. Like, what does it mean when you're tracking a vacuum if someone takes apart the handle and the bottom part?
Yeah,
I think
it's even worse. I was talking, there's a sequence called Epic Kitchens, and then they are sort of cooking. So they cut the banana into 2, and which one do you track? Well, they labeled it the one which is in contact with the hand, and the other part is sort of like, but how do you know? And then you cut the banana into 4 pieces. Which one? So maybe we have to somehow say, well, just linear association is not good enough. And of course, when you put if you take 3 potatoes and create potato mesh out of that, then the tracking sort of like becomes something else. Yeah. So yeah, there are our model of what can happen in the world by saying this is an object and it has sequence of poses doesn't cover everything.
Yeah, totally agree. Hopefully, a few years from now, someone will build a new data set and they'll figure out the answers to those questions and be able to point back at Tau and say, they didn't even bother to label these things that break apart.
Okay. Okay.
Okay, then at this stage, I think we have to move to our last speaker. So I would like to thank Jiri again for your great talk, and we will talk again soon in the second session. Okay, so now we are at the last talk of this first session, and here I'm very excited to announce Bastian Leibe as our next speaker. So Bastian is a full professor at RWTH Aachen University, where he leads the computer vision group. He holds a master's degree from Georgia Institute of Technology, a diploma degree from the University of Stuttgart, and a PhD from ETH Zurich, so all in computer science. Bastian was also a postdoctoral researcher at the Technical University of Darmstadt and at ETH Zurich, where he developed several methods for multi-object detection and tracking for mobile platforms, as well as for 3D shape modeling and registration. Over the years, Bastian received several awards for his research work, including the Virtual Reality Best Paper Award in 2000, the ETH Medal and the DGM Main Prize in 2004, CVPR Best Paper Award in 2007, DGM Olympus Prize in 2008, the ICRA Best Vision Paper Award in 2009, and the ICPRS Journal of Photogrammetry and Remote Sensing Best Paper Award in 2010. And he's also a great PhD supervisor.
And welcome to my presentation. My name is Bastian Leibe, and I will be talking about tracking as a cue for object discovery. The work I will be presenting was to a large extent done by my former PhD student Alyosha Osheb, who is now doing a postdoc at TU Munich, as well as my current PhD students Ali Attar and Sabarinat Mahadevan. Throughout the field of tracking, in particular multi-object tracking, what we are seeing is the striking success of the tracking by detection scheme. Throughout different benchmarks, many different tasks, tracking by detection approaches are the most prominent class of approaches, and they're dominating many of those benchmarks. So clearly a huge part of the success of tracking in the last few years was due to better object detectors. In particular, better deep learning based object detectors that have brought huge improvements over the last few years. So one could rightfully ask, are we done yet? Was this all? Do we still have to continue working on tracking, or should we just improve the object detectors and this will solve all the tasks? The following picture shows that this is not the case. What you're seeing here is the crash site of a Tesla car that was running on autopilot and that hit a static fire truck at full speed. So apparently what happened here was that the Tesla's radar sensors failed to pick up the fire truck as an obstacle, and its vision system didn't recognize the fire truck because it didn't have a notion of what a fire truck is. So here clearly this is a case where something very bad happened because of a failure of the object detection system to recognize an important obstacle. And clearly one could think about improving the object detector, maybe then running a software update to also include other objects that turn out to be also important. But if you think about building a safe autonomous car, this is clearly not an option. So for such scenarios, we really need to have fallback options. We need to have tracking systems that can also cope with detection failures. And there are many similar scenarios. In real application scenarios, the problem is that there are many object categories available for which we neither have good detectors yet, nor sufficient training data, because those objects occur very rarely. And this is even more of a problem in robotic scenarios, where each robotic deployment site may be different, and it may again contain novel objects that you might not have seen in any of the previous deployments and that therefore are not in your training set. So here clearly it is it would be a very expensive option to go through and run a data collection effort every time you need to start a new deployment. So the question here is really, how can we learn the relevant objects without costly annotation? In order to put this question into perspective, let's go back in time for some 20 years. And if you look at typical tracking systems from back then, they were mostly based on background modeling. So here you had a static camera, a background model that was learned more or less complex, and the background model really solved the task of figure ground segmentation. So what remained after background modeling was just blob tracking. And what we saw here was the emergence of relatively simple but still very effective tracking systems. And this was possible because the background modeling acted as a filter to make the problem feasible. Now, if you look at today's tracking pipelines, in particular at tracking by detection schemes, here object detectors have taken over the role of the big filter. They effectively solve the figure ground segmentation problem for us, and this made it possible for the tracking community to focus on data association problems and mainly be concerned about how to put the different detections into a coherent order. But this directly raises the questions, what can we do if we don't have detectors available? How can we address tracking in such a case? And this question is what I want to address here in my talk today. So the goal I want to explore today is to go towards generic object tracking. That means tracking of objects for which we may not have detectors available. However, this means we are removing the big filter. Tracking by detection only works if object detectors are available, so if we take away those detectors, we need to think about alternative schemes how to perform tracking. And this leads us to some additional questions, namely, can we extract generic object candidates from appearance and depth alone and robustly track them? And is a tracking before detection scheme, where we first track and then extract the tracks and classify them, a viable option? Can we do this in a way that is competitive on current benchmarks? In order to address this question, I want to present 3 recent lines of work from our group. The first is a category-agnostic multi-object tracking approach, which was developed by Alyosha Oshep during his PhD thesis. After that, I will focus on the video instance segmentation problem, and here I will present an approach that you will see at this conference at ECCV on Wednesday, which treats tracking as a bottom-up spatial temporal grouping problem. And finally, I will present a study where we used the category-agnostic multi-object tracker for large-scale video object mining in order to perform object discovery. And this is a proof-of-concept study where we wanted to see how far can we get and whether those object tracks that we can obtain with such a category-agnostic tracker are suitable for object discovery. So let's start with the category agnostic multi-object tracking approach, or CAMOT. The main idea behind this approach is that we start from a set of low-level region proposals. Over the course of our work, we've experimented with different region proposal generators, first with sharp mask and then later on with mask RCNN. We start by extracting an overcomplete set of such region proposals, and then we try to track each region proposal over time, while applying a number of consistency filters. So essentially, we want to filter out those region proposals whose contour does not move consistently with the effects of perspective and ego motion. We do this by first projecting each of the extracted regions onto a stereo point cloud. We then apply optical flow or scene flow in order to predict how the corresponding 3D points will likely move within the next frame, considering also our ego motion. And then we project the resulting predicted point clouds back into the image, and this results in a predicted contour. We then compare this predicted contour with the contours of the region proposals in the next frame using a mask intersection over union criterion. And this will give us a data association that we can then use for tracking. It turns out that this mask intersection over union is already a very powerful cue for data association. When we apply this approach based on mask RCNN proposals, here for known object categories, you can see that this is already sufficient to give us very stable tracking results over time. We've also evaluated the quantitative performance, and we found that this tracking approach achieves state-of-the-art tracking performance, at least in the close range of 25 to 30 meters distance where stereo information is available. For this range, we get accurate instance segmentation and 3D localization for all tracked objects. We have also recently presented an extension of the CAMOT approach towards video instance segmentation. The resulting approach is called 4D generic video tubes, or 4D GVT, and it produces a temporally consistent 3D instance segmentation of all tracked objects over an entire video sequence. A key improvement compared to CAMOT is a better sequence level track optimization in order to return more stable trajectories. In the following, I will present the 4D GVT results because we have some better visualizations for them. What you see here are the frame level object proposals that we start from. In order to make sure that we don't miss any object, we start from a large number of such proposals, typically 100 to 200, and then we continue to track those proposals over time, applying our consistency checks, and this manages to filter out a large number of false positives or mismatches, resulting in a reduced set of 3D volumes that are consistent over a certain time. Here is now a visualization of the resulting video tubes when we only visualize those tubes that correspond to cars and pedestrians. So here you can see that this looks just like regular car tracking in the kitty scenario. And here are now the resulting video tubes when we keep all tracks from known and unknown objects. And in particular, what you can see now is that the approach manages to track both the known categories, cars, pedestrians, but also a large number of unknown object categories which still make sense. So we get tracks for traffic lights, for street signs, for parts of street furniture, here for different warning beacons on the street. All of those are interesting object categories for a driving scenario, but they were not in the category set that maskRNN was trained on. So essentially, 40GVT is a high-performing generic object proposal generator, but it operates at the video sequence level instead of at the frame level. So you just give it a video sequence and it produces a set of output tracks together with video instance segmentations for each tracked object. And those object tracks contain both known objects and potentially interesting unknown objects. If you want to play around with it, code is available at the following link, so give it a try. Next, we present our approach for creating spatio-temporal embeddings for video instance segmentation. Prior approaches to video object segmentation mainly follow one of two strategies. One class of approaches uses a mask propagation strategy. Prior approaches to video object segmentation can generally be grouped into two main strategies. The first group uses a mask propagation scheme. Here it is assumed that the first frame ground truth mask is given, and the task then becomes to propagate this mask to all future frames. The second class of approaches uses a proposal tracking by detection scheme. So here this class of approaches starts with an instance segmentation step, and then these instance segmentations are associated over time. This scheme is quite similar to what CAMOT and 40GVT did in our previous discussions. And in fact, BREM was one of the first state-of-the-art VOS approaches that used this proposal tracking by detection scheme, was heavily influenced and inspired by CAMOT. In contrast, in our approach called STEMSEG, which stands for Spatial-Temporal Embeddings for Segmentation, we follow different design goals. First, we assume that no first frame ground truth mask is given. In addition, we also want to avoid the two-step tracking by detection approach and instead create a one-step approach that can efficiently be trained end-to-end. So in contrast to previous approaches, STEMSEG adopts a novel strategy and associates pixels jointly across space and time in a bottom-up manner. The main ideas in STEMSEG are the following. First, we model a video clip as a single 3D spatial-temporal volume. For each pixel in the spatial-temporal volume, we then learn per pixel embeddings for the entire input clip. Here the idea is that embeddings belonging to the same object instance should be very close, so they should form a tight cluster. We model those clusters by Gaussian distributions. We realize this strategy using a novel embedding formulation and a single-stage network architecture that lends itself to end-to-end training. Here is a visualization of our task formulation. STEMSEG takes as input an entire video clip of up to T frames, which is then processed together in a 3D CNN with an encoder-decoder architecture. The CNN produces three distinct outputs. The first output is an embedding value for each pixel in the spatial-temporal volume. In addition, we also estimate for each pixel the cluster variance of the grouped embeddings if this pixel were the object center. And then finally, we estimate a cluster center heat map that is used in order to initialize the search for objects. For example, if we used two-dimensional embeddings here, then we would expect to see for this scene here two clusters. One cluster for the rider, the other one for the horse. We model those clusters as having a Gaussian shape, meaning that they can be described by a mean and a variance in embedding space. During inference, we first consider the inferred 3D heat map for the center positions of all object candidates, and we retrieve peaks in this spatial-temporal heat map as object seeds. For each peak, we then look up the corresponding embedding values and variances, and this gives us an estimate for the cluster mean and variance. And all spatiotemporal pixels that produce embedding values that fall under the estimated Gaussian distribution are taken as belonging to the segmentation of the same object track. We train our network using a combination of 3 loss functions. First, we use a Lovász loss function for the embeddings in order to maximize the IOU between the predicted and ground truth masks. In addition, we adopt a variance smoothness loss in order to encourage the variance values that are produced at every object pixel to be as similar as possible. Finally, we add a heat map loss that regresses the output at every object pixel to be the same as the probability of the embedding at that coordinate. Altogether, we thus end up with a very simple approach that can be trained in an end-to-end fashion. However, a main issue in practice is that we need to process an entire video clip at the same time with a 3D network. In order to handle that, we need to use a powerful spatiotemporal encoder-decoder architecture. Our encoder is a 2D ResNet 101 backbone with a feature pyramid network stacked on top. For every frame, this encoder produces 4 feature maps at different spatial resolutions. To effectively learn spatiotemporal embeddings from those feature maps, we propose a novel spatiotemporal squeeze-excite decoder with 3D convolutions. We first stack the feature maps along the temporal dimension. Then we perform a series of 3D convolution and temporal pooling operations in order to obtain spatiotemporal features. We then upsample and concatenate the results with the next higher resolution, and the process is completed in several steps until it produces the final output. Here you see a visualization of the video sequence together with the spatiotemporal embeddings in 2 projections that are produced. As you can see, our approach is able to separate different object instances and to produce unique clusters in embedding space. Those embeddings then correspond to video instance segmentations that are consistent over a length of the video. And this is the case for different datasets. Here we show results for Davis and YouTube Viz. Here we show results on Kitty Mods, and you can see that the approach is able to adapt to this multi-object tracking scenario and to produce multi-object tracking and segmentation results that are very consistent over time. Again, all of this is done using bottom-up spatiotemporal grouping. There are no distinct object detectors that would be applied here. We also evaluated our approach on several benchmarks and for several segmentation tasks and obtained state-of-the-art results without needing major adaptations. Please see our paper in the poster session on Wednesday morning for details about the approach and the detailed results. In conclusion, I've presented you StemSec as an instance of an approach that performs tracking as a spatial-temporal grouping procedure. StemSec can be applied both for video object segmentation, video instance segmentation, and multi-object tracking and segmentation tasks without requiring adaptations of the basic procedure. Finally, I want to quickly present some results of a proof of concept study that we have performed using the category agnostic multi-object tracking results in order to perform large-scale video mining for object discovery. The goal of this study is to evaluate whether we can discover new object categories from raw video data simply by using tracking as a data generation method for performing self-supervised learning. If this were possible, this would solve many practical issues in automotive applications and mobile robot deployment, so there is a great interest in this question. in order to perform this experiment, we apply our category-agnostic multi-object tracking procedures for large-scale object mining from video. In detail, we have applied CAMOD and later on also 40GBT to large video corpora showing driving scenes from the Oxford robot car dataset. So this, in total, we had a dataset of 9 hours of video from Oxford robot car, and you can see some of the resulting sequences and some of the resulting tracks and generic video object tubes that were extracted here. Our goal is now to take those video tubes and use them in order to first evaluate what kind of objects can we track and whether there are objects that are still unknown for which we currently don't have detectors, and then to test out whether we can use simple clustering techniques in order to extract clusters of coherent objects that we could train detectors on. For this study, we have annotated a subset of tracks. We've used a subset, we have used the Kitty dataset in order to first see what is available in this well-known Kitty data. And then we've annotated a subset of our sequences from Oxford. And in both cases, we've annotated the tracks that we have extracted using category agnostic tracking. What you see here now are two histograms of the number of occurrences for different classes. In red are classes that are known from the COCO set. In blue are classes that are not reflected in COCO. And what becomes directly visible is that there is a large number of object classes that can be extracted using such a category agnostic tracking procedure, and for which enough examples are in the set to train additional detectors. What also becomes visible is that at some point there are simply too few examples left in this amount of video. So in order to perform large-scale training, we would need to also process larger corpora of video. Both 40GBT and CAMOD are suitable for this task. Here we have processed 10 hours of video, but in principle, there is no limit on the number there's no limit on the amount of video you can process given some clusters. Both approaches are quite efficient for this task. Here are some example object discovery tasks. For this, we have taken subsets of the tracks and we have applied clustering based on the raw network outputs. Here you can see that from this simple appearance-based clustering, we are already able to extract some interesting object categories, such as transformer boxes or this kind of striped sign. From Oxford, we have well-defined clusters of traffic cones and sign bollards. So all of those are potentially interesting categories that it would make sense to train detectors on. And here they are extracted entirely from a self-supervised setup. So in conclusion, we've posed the question whether we can track generic unknown objects robustly. And the answer is a clear yes. We've shown state-of-the-art video object segmentation results using a bottom-up clustering approach, and we've shown a robust generic tracking pipeline that is applicable for street scenes. In addition, I've shown you results of a proof-of-concept study where we have used this category-agnostic tracking for large-scale video mining, demonstrating that we can perform object discovery. So I believe that this opens up interesting applications in automotive and mobile robotics, but there are still a number of fundamental research questions that remain. In particular, one open question is how to deal with the long tail of the object distribution, where there are very few examples simply because objects are very rare. And also an open question is how can we use those results in order to refine existing detectors without sacrificing performance on the well-known classes. Also, we've only dealt with things classes here, so new stuff categories are still not captured by this setup. With this, I've reached the end of my presentation. Thank you very much for your attention.
Okay, so I would like to thank Bastian for this talk. Bastian unfortunately couldn't be here today due to higher order constraints, but if he could, he would definitely join us. So we are now a bit, I think we are like 20-25 minutes over length, right?
Yeah, I think that's right.
Yeah. So yeah, I would be totally ready to stay here longer and answer potential questions, both regarding talk from Laura and Bastian.
I guess there's a few questions for Laura's talk. Maybe it's best for you to just type out the answers. And maybe we officially close off the session, but then we stick around afterwards. So people have questions, they can stick around, but if not, feel free to leave and join us for the next session.
Wait, can you see my screen?
Yep.
Does it show schedule session 2?
Yeah.
Okay.
Yeah.
Okay, so I guess we can keep taking the questions until after we officially close the first session of the workshop. I would once again like to thank all the speakers for a spirited discussion on bringing different object tracking communities back together. We will reconvene for session 2 at 3 p.m. Eastern time, or I think that's 8 p.m. British summer time. So session 2 will see talks from Anju Kanadzawa, Deva Ramanan, and Ross Gershik. And we have a very rich discussion coming up in the roundtable. So see you all in a few hours.